Chapter 1. Orientation and the Fundamentals You Cannot Afford to Forget. Welcome. This is your audio study guide for the ECE1004 Cumulative Final Exam at Virginia Tech Introduction to Electrical and Computer Engineering. Here is how this recording is built. First, we go through the fundamentals: charge, current, voltage, power, and the sign conventions that trip people up. Then we walk through every single problem in your final exam practice pocket, out loud, step by step, with all the numbers spoken so you can follow along without looking at anything. Then we cover the material that is very likely to appear on the final but is not in the practice pocket: Thevenin and Norton equivalents, superposition, maximum power transfer, the full family of operational amplifier circuits, first-order RC and RL transient response, number systems, and two's complement arithmetic, Carnot maps, and the standard combinational logic building blocks. At the end, there is a rapid-fire drill where I ask you a question, give you a few seconds of silence, and then give you the answer. That last part is the single most useful thing you can do while driving. You do not need a pencil. Everything is spoken. If a number matters, I will say it twice. Let us begin with the absolute foundation. Charge. The symbol is Q. The unit is the coulomb, abbreviated capital C. One electron carries a charge of negative 1.602 times 10 to the negative 19th coulombs. Charge is conserved. It is never created and never destroyed in a circuit. It only moves. Current. The symbol is lowercase I or capital I when it is a constant direct current. Current is the time rate of flow of charge past a point. In equation form, I equals dq dt, the derivative of charge with respect to time. The unit is the ampere, abbreviated capital A, and 1 ampere is 1 coulomb per second. Here is the classic conceptual trap. Conventional current flows in the direction that positive charge would move. Electrons actually move the opposite way. Every equation you write in this class uses conventional current. Do not try to reason with electrons. Use conventional current, always. If current is a function of time, then charge is the integral of current. Q equals the integral of I dt. Current and charge are related by calculus in both directions. Differentiate charge to get current. Integrate current to get charge. Remember that pairing, because the exact same relationship shows up again with capacitors and inductors. Voltage. The symbol is lowercase v or capital V. Voltage is energy per unit charge. V equals dW dq, the derivative of energy with respect to charge. The unit is the volt, abbreviated capital V, and 1 volt is 1 joule per coulomb. Voltage is always measured between 2 points. There is no such thing as the voltage at a point unless you have already declared a reference node, which we call ground. When your problem says the voltage at node 2 is 4.25 volts, what it really means is the voltage at node 2 measured with respect to ground. Power. The symbol is P. Power is the rate at which energy is delivered or absorbed. P equals dW dt, and for circuit elements, it becomes the beautifully simple product P equals V times I, voltage times current. The unit is the watt, abbreviated capital W, and 1 watt is 1 joule per second. Energy. The symbol is W. Energy is the integral of power over time. W equals the integral of P dt. The unit is the joule. In electric utility billing, it is the kilowatt hour, which is 3.6 million joules. Now, the passive sign convention. This is the single most common source of lost points on an ECE1004 exam. So listen carefully. The passive sign convention says, if current enters the element at the terminal you have marked with a plus sign, then the power computed as P equals V times I is the power absorbed by that element. Positive power absorbed means the element is consuming energy, turning it into heat or storing it. Negative power absorbed means the element is actually delivering energy to the rest of the circuit. That is what a battery or a source does. Say it to yourself this way: current in at the plus, power absorbed. Current in at the minus, power delivered. Resistors always absorb positive power. A resistor cannot generate energy. If you compute a negative absorbed power for a resistor, you have made a sign error. That is a free error check, and you should use it on the exam. Here is another free check. In any complete circuit, total power delivered equals total power absorbed. Add up the power absorbed by every element in the circuit, including sources, and the sum must be 0. This is conservation of energy, and it is a powerful way to verify a full circuit solution when you have time left at the end of an exam. Let us talk about units and prefixes, because the practice pocket uses kilo ohms and milliamps, and mixing them up will destroy an otherwise perfect solution. The prefixes, from big to small. Tera is 10 to the 12th. Giga is 10 to the 9th. Mega is 10 to the 6th. Kilo is 10 to the 3rd, that is 1,000. Then unity. Then milli is 10 to the negative 3rd, 1,000th. Micro is 10 to the negative 6th, 1,000,000th. Nano is 10 to the negative 9th. Pico is 10 to the negative 12th. Femto is 10 to the negative 15th. Now here is the trick that saves you enormous time, and it is the trick your practice pocket uses in the nodal analysis problem. Volts divided by kilo ohms equals milliamps. Let me repeat that, because it is worth actual points. Volts divided by kilo ohms gives you milliamps directly. Why does that work? Because kilo is 10 to the 3rd and milli is 10 to the negative 3rd, and they cancel. So if every resistor in your circuit is written in kilo ohms, and every source is in volts, you can just drop the K and the M entirely, do all the arithmetic with bare numbers, and your answers come out in volts and milliamps automatically. That is exactly what the solution to problem 3 does when it writes the node equations with a 4, a 3, and a 2 in the denominators instead of 4,000, 3,000, and 2,000. Similarly, volts divided by mega ohms gives microamps. Volts times microfarads gives microcoulombs. Learn the consistent unit sets and stop carrying powers of 10 around. Now Ohm's law, the most used equation in the entire course. V equals I times R, voltage equals current times resistance. The unit of resistance is the ohm, and the symbol is the capital Greek letter omega. Rearranged, I equals V over R, and R equals V over I. Ohm's law applies to a resistor, and the voltage and current in that equation must obey the passive sign convention. If current flows into the plus terminal, then V equals IR with a positive sign. If your assumed current flows into the minus terminal, then V equals negative IR. Most of the time you will just define the current to flow from plus to minus through the resistor and never think about it again, and that is fine, as long as you are consistent. Conductance. The symbol is capital G. Conductance is the reciprocal of resistance. G equals 1 over R. The unit is the Siemens, abbreviated capital S. Older textbooks call it the mho, which is ohms spelled backwards. In terms of conductance, Ohm's law reads I equals G times V. Conductance is convenient in nodal analysis because when you write a node equation, you naturally add up conductances. Power in a resistor. There are 3 equivalent forms, and you should know all 3 cold, because on an exam you will sometimes know the current and sometimes know the voltage. Form 1. P equals V times I. Form 2. P equals I squared times R. That is current squared times resistance. Form 3. P equals V squared divided by R. That is voltage squared over resistance. Note the squares. Power scales with the square of current and with the square of voltage. Double the current through a resistor and you quadruple the heat. That is why transmission lines run at very high voltage and low current. To cut the I squared are losses. 2 special cases you must recognize instantly. A short circuit is a resistance of 0 ohms. The voltage across a short is always 0, no matter how much current flows through it. A short circuit is an ideal wire. If a resistor is shorted out by a wire in parallel with it, that resistor carries no current, and you can erase it from the circuit. An open circuit is a resistance of infinity. The current through an open is always 0, no matter what voltage appears across it. If an element is in series with an open, no current flows in that branch at all, and you can erase that branch. But note carefully, the voltage across an open circuit is generally not 0. That is exactly what you compute when you find a Thevenin open circuit voltage. Now the sources. An ideal independent voltage source maintains a specified voltage across its terminals no matter what current flows through it. It is drawn as a circle with a plus and a minus, or in some textbooks as a battery symbol with long and short bars. The current through a voltage source is whatever the rest of the circuit demands. You do not know it in advance, and you cannot compute it with Ohm's law. You find it from KCL. An ideal independent current source forces a specified current through its branch no matter what voltage appears across it. It is drawn as a circle with an arrow inside. The voltage across a current source is whatever the rest of the circuit demands. You do not know it in advance, and you find it from KVL. Dependent sources, also called controlled sources, are drawn as diamonds instead of circles. There are 4 kinds: voltage-controlled voltage source, current-controlled voltage source, voltage-controlled current source, current-controlled current source. The value of a dependent source is proportional to a voltage or current somewhere else in the circuit. If your exam has a dependent source, the key rule is this: write your node or mesh equations exactly as you normally would, treating the dependent source value as an unknown symbol, and then add one extra equation that expresses the controlling variable in terms of your node voltages or mesh currents. That extra equation is what makes the system solvable. Never leave a controlling variable in your final equations. Always substitute it out. 2 more definitions that exam questions love to test directly. A node is a point of connection between 2 or more elements. More precisely, a node is an entire stretch of continuous wire, including any junctions along it. If 2 points are connected by nothing but perfect wire, they are the same node, no matter how far apart they are drawn on the page. When a question asks how many nodes are in this circuit, redraw the wires and count the distinct copper regions, not the dots. A loop is any closed path through the circuit that does not pass through any node more than once. A mesh is a loop that contains no other loop inside it. Think of a mesh as a window pane in the circuit diagram. When you do mesh analysis, you write one equation per window pane. And finally, the 2 conservation laws that everything else in this course is built on. Kirchhoff's current law, KCL. The algebraic sum of currents entering a node equals 0. Equivalently, the sum of currents flowing in equals the sum of currents flowing out. This is conservation of charge. Charge does not pile up at a junction of wires. Kirchhoff's voltage law, KVL. The algebraic sum of voltages around any closed loop equals 0. Equivalently, the sum of voltage rises equals the sum of voltage drops. This is conservation of energy. If you walk all the way around a loop and come back to where you started, you must be back at the same potential. KCL is about nodes and currents. KVL is about loops and voltages. Nodal analysis is built on KCL. Mesh analysis is built on KVL. If you remember which law drives which method, you will never start a problem in the wrong direction. That is the foundation. In the next chapter, we build series and parallel combinations, the voltage divider, and the current divider, and then we go straight into problem 1 of the practice pocket. Chapter 2. Series, parallel, and the divider rules. Almost every resistive circuit problem on this exam starts with the same move. Collapse the network down to something simple, find the total current, and then expand back outward to recover the individual voltages and currents. To do that fluently, you need series and parallel combinations and the 2 divider rules in your bones. Series first. 2 elements are in series if they share exactly one node and no other element is connected to that shared node. The defining consequence is that series elements carry the same current. Not the same voltage, the same current. There is nowhere else for the charge to go. For resistors in series, resistances add. Our equivalent equals are 1 plus, are 2 plus, are 3, and so on for as many as you have. Series resistance is always larger than the largest individual resistor. Voltage sources in series add algebraically. If 2 10-volt sources are in series with their plus terminals pointing the same way around the loop, they act as a 20-volt source. If they oppose, they cancel to 0. Parallel next. 2 elements are in parallel if they share both of their nodes. Both ends of one connect to both ends of the other. The defining consequence is that parallel elements have the same voltage across them. Not the same current, the same voltage. For resistors in parallel, the conductances add, which means the reciprocals of resistance add. 1 over R equivalent equals 1 over R1 plus 1 over R2, and so on. For exactly 2 resistors in parallel, there is a shortcut you will use constantly. R equivalent equals the product over the sum. R1 times R2, divided by R1 plus R2. Say it out loud, product over sum. But be careful, product over sum works for exactly 2 resistors. It does not work for 3. For 3 or more, either use reciprocals or combine 2 at a time. 4 identical resistors of value are in parallel. The equivalent is simply R divided by N. Two 100 ohm resistors in parallel give 50 ohms. Three 60 ohm resistors in parallel give 20 ohms. Parallel resistance is always smaller than the smallest individual resistor. That is your sanity check. If you combine a 37 ohm and a 45 ohm resistor in parallel and get anything larger than 37, you have made an arithmetic mistake. The true answer must be below 37. Current sources in parallel add algebraically, respecting arrow direction. Now, the voltage divider. This applies to resistors in series. If a voltage V total is applied across two series resistors R1 and R2, then the voltage across R1 is V total times R1, divided by the quantity R1 plus R2. In words, the total voltage splits between series resistors in direct proportion to their resistance. The bigger resistor gets the bigger share of the voltage. If R1 is 3 times R2, then R1 takes 3/4 of the voltage and R2 takes 1/4. The general form for a chain of many series resistors. The voltage across resistor Rk equals V total times Rk divided by the sum of all the resistances in the chain. Now, the current divider. This applies to resistors in parallel. If a total current I total enters a parallel pair R1 and R2, then the current through R1 equals I total times R2, divided by the quantity R1 plus R2. Look carefully at that. To find the current in R1, you put the other resistor, R2, in the numerator. That is the opposite of the voltage divider, and it catches people every single semester. The reason is physical. Current takes the path of least resistance, so the smaller resistor gets the larger share of the current. Say it out loud. Voltage divider, same resistor on top. Current divider, other resistor on top. For more than two resistors in parallel, the cleanest approach is to find the voltage across the parallel combination first, then apply Ohm's law to each branch individually. That is exactly what the practice pocket does in problem 1, and it is more reliable than trying to write a three-way current divider from memory. Now, a critical warning about identifying series and parallel. Students lose points not because they cannot do the arithmetic, but because they misidentify the topology. Test for series. Do these two elements carry the identical current, with nothing tapping off in between? If there is a junction between them where a third wire leaves, they are not in series. Test for parallel. Are both terminals of one element connected by pure wire to both terminals of the other? If yes, parallel. Drawing position on the page means nothing. Two resistors drawn on opposite sides of a diagram can absolutely be in parallel, and two resistors drawn side by side and touching may not be. A useful technique. Label every node with a letter A, B, C, and so on, where each distinct stretch of wire gets one letter. Then write each resistor as a pair of node labels. Every resistor that reads A to B is in parallel with every other resistor that reads A to B. That method never lies to you, and it takes about 30 seconds. One more combination rule to know, because it appears in ladder networks. When you reduce a ladder, you always start at the end farthest from the source and work backwards toward the source. You cannot start in the middle. Reduce the far end, absorb it, step one rung closer, reduce again, and keep going until you have one resistor. Let us also handle a special case that shows up on exams as a trick. If a resistor has both ends connected to the same node, meaning it is shorted out, then it has 0 volts across it. It carries 0 current, and you can delete it. If a resistor is in series with an open circuit branch, it carries 0 current, so it has 0 volts across it, and you can delete it too. But note that deleting it does not mean the two ends are at the same potential once you look at the wider circuit. And the bridge case. If you have a Wheatstone bridge configuration, 5 resistors arranged as a diamond with 1 across the middle, and the bridge is balanced, meaning R1 over R2 equals R3 over R4, then the middle resistor carries 0 current. You can remove it or short it, whichever is more convenient, and then the network becomes simple series parallel. If the bridge is not balanced, no amount of series parallel reduction will work, and you must use nodal or mesh analysis, or a Y-delta transformation. Since we have mentioned it, here is the Y-delta transformation briefly, in case it appears. A Y, also called a T, is 3 resistors meeting at a common center point. A delta, also called a pi, is 3 resistors forming a triangle. Delta to Y Each Y resistor equals the product of the two adjacent delta resistors divided by the sum of all three delta resistors. So R1 of the Y equals RB times RC over the quantity RA plus RB plus RC. Y to delta. Each delta resistor equals the sum of the pairwise products of the Y resistors divided by the opposite Y resistor. So RA of the delta equals R1 R2 plus R2 R3 plus R3 R1, all divided by R1. Special case worth memorizing. If all three delta resistors are equal to R delta, then all three Y resistors are equal to R delta divided by 3. And going the other way, R delta equals 3 times R Y. Now let us put series, parallel, and the dividers to work on the first problem in your practice pocket. That is the next chapter. Chapter 3. Practice Pocket Problem 1 and Problem 2. Problem 1. The setup. We have a 24-volt battery. Coming out of the battery's positive terminal, there is a single resistor R1 of 80 ohms in series with everything else. After R1, the circuit splits into two parallel branches, and then both branches come back together and return to the battery's negative terminal. The upper branch contains R2, 49 ohms, in series with R3, 51 ohms. The lower branch contains R4, 37 ohms, in parallel with R5, 45 ohms, and that parallel pair is in series with R6, 75 ohms. We want the voltage across and the current through every resistor. 6 resistors, 12 numbers. Let us go. Step 1. Collapse the upper branch. R2 and R3 are in series, because the current that leaves R2 has nowhere to go except into R3. Series resistances add. R23 equals 49 plus 51, which is 100 ohms exactly. Nice round number. R23 equals 100 ohms. Step 2. Collapse the parallel pair in the lower branch. R4 and R5 are in parallel, so we use product over sum. R45 equals 37 times 45, divided by 37 plus 45. 37 times 45 is 1,665. 37 plus 45 is 82. So R45 equals 1,665 over 82, which is 20.305 ohms. Sanity check that immediately. 20.3 ohms is smaller than 37, the smaller of the two. Good. Parallel must always come out below the smallest branch. Step 3. Finish the lower branch. That 20.305 ohm equivalent is in series with R6, which is 75 ohms. R456 equals 20.305 plus 75, which is 95.305 ohms. Step 4. Combine the two branches. Now, after R1, we have two branches in parallel, 100 ohms on top and 95.305 ohms on the bottom. Product over sum again. Our parallel equals 100 times 95.305, divided by 100 plus 95.305. The numerator is 9,530.5. The denominator is 195.305. Divide, and you get 48.798 ohms. Sanity check. 48.8 is less than 95.3, the smaller branch. Good. And notice, when two nearly equal resistors are in parallel, the result is close to half of either one. 195 are nearly equal, and half of about 97 is about 48.8. That matches. That is a fast mental check you can do on an exam. Step 5. Total resistance. R1 is in series with that whole parallel combination. Our total equals 80 plus 48.798, which is 128.798 ohms. Step 6. Total current by Ohm's law. I total equals the source voltage divided by the total resistance. 24 volts divided by 128.798 ohms equals 0.18634 amperes. That is about 186 milliamps. Let me repeat. I total is 0.18634 amps. Step 7. R1. R1 is in series with the entire rest of the circuit, so every bit of current from the battery passes through it. Therefore, the current through R1 equals the total current, 0.18634 amps. The voltage across R1 is Ohm's law. V equals I times R. 0.18634 times 80 equals 14.907 volts. So V across R1 is 14.907 volts. Step 8. The voltage across the parallel section. By KVL around the source loop. The 24 volts of the source is split between R1 and the parallel network. So the parallel network sees 24 minus 14.907, which equals 9.093 volts. Call that V parallel, 9.093 volts. And here is the important part. Because those two branches are in parallel, both branches see that same 9.093 volts. The upper branch and the lower branch each get exactly 9.093 volts across them. Step 9. The upper branch currents and voltages. Current in the upper branch equals V parallel divided by R23. 9.093 divided by 100 equals 0.09093 amps. That is 90.93 milliamps. Because R2 and R3 are in series, they both carry that same current. So the current through R2 equals the current through R3 equals 0.09093 amps. Voltage across R2, 0.0909, 3 times 49 equals 4.456 volts. Voltage across R3, 0.0909, 3 times 51 equals 4.637 volts. Check. 4.456 plus 4.637 equals 9.093 volts, which is exactly the branch voltage. KVL confirmed. Also notice that R3, being slightly larger, took slightly more voltage. That is the voltage divider behaving exactly as it should. Step 10. The lower branch. Current in the lower branch equals V parallel divided by R456. 9.093 divided by 95.305 equals 0.09541 amps. About 95.4 milliamps. R6 is in series with the parallel pair, so R6 carries that whole branch current. Current through R6 is 0.09541 amps. Voltage across R6 equals 0.09541 times 75, which equals 7.156 volts. Step 11. The parallel pair R4 and R5. The remaining voltage in that branch goes across the parallel pair. V across R4 and R5 equals 9.093 minus 7.156, which equals 1.937 volts. Because R4 and R5 are in parallel, they share that voltage. So the voltage across R4 is 1.937 volts, and the voltage across R5 is also 1.937 volts. Same voltage, different currents. Current through R4 equals 1.937 divided by 37, which equals 0.05236 amps, or 52.36 milliamps. Current through R5 equals 1.937 divided by 45, which equals 0.04305 amps, or 43.05 milliamps. Check with KCL. 52.36 plus 43.05 equals 95.41 milliamps, which is exactly the branch current we computed. Beautiful. And notice R4, the smaller resistor, got the larger current. Current divider behaving correctly. Final check with KCL at the top split. The upper branch carries 90.93 milliamps. The lower branch carries 95.41 milliamps. Add them. 186.34 milliamps, which is exactly the total current through R1. Every law checks out. Let me summarize problem 1, all 12 numbers. R1, 80 ohms, current 186.3 milliamps, voltage 14.91 volts. R2, 49 ohms, current 90.93 milliamps, voltage 4.46 volts. R3, 51 ohms, current 90.93 milliamps, voltage 4.64 volts. R4, 37 ohms, current 52.36 milliamps, voltage 1.94 volts. R5, 45 ohms, current 43.05 milliamps, voltage 1.94 volts. R6, 75 ohms, current 95.41 milliamps, voltage 7.16 volts. If you want one more layer of confidence, check power. The source delivers 24 volts times 0.18634 amps, which is 4.472 watts. And if you add up I squared R for all 6 resistors, You get the same 4.47 watts. Energy is conserved. The technique to internalize from problem 1 is this rhythm. Collapse inward to a single resistance, get the total current, then expand back outward, alternating between KVL to find branch voltages and Ohm's law to find branch currents. Every ladder problem in this course follows that rhythm. Now, problem 2. The setup. There is a source of unknown voltage, Vx, on the left. From its positive terminal, a 5-ohm resistor runs to the right in series. After that 5-ohm resistor, 3 elements hang in parallel down to the bottom rail. A 10-ohm resistor, then a 5-ohm resistor, then a rightmost 5-ohm resistor. We are told the rightmost 5-ohm resistor carries exactly 1 ampere flowing downward. Find Vx. This is a back-to-front problem. We do not know the source, but we do know one branch current. So we work backwards from the known branch to the source. That structure is extremely common on exams, and it is called a ladder or back substitution problem. Step 1. The rightmost branch. That 5-ohm resistor carries 1 amp. So by Ohm's law, the voltage across it is V equals I times R equals 1 times 5, which is 5 volts. Step 2. Recognize what that voltage means. That rightmost 5-ohm resistor is connected between the top rail and the bottom rail. So are the middle 5-ohm resistor and the 10-ohm resistor. All 3 are between the same 2 nodes, so all 3 are in parallel. So all 3 have exactly 5 volts across them. Step 3. The middle 5-ohm branch. Its current is 5 volts divided by 5 ohms, which equals 1 amp. Step 4. The 10-ohm branch. Its current is 5 volts divided by 10 ohms, which equals 0.5 amps. Step 5. KCL at the top node. All the current that comes through the series 5-ohm resistor has to split among those 3 parallel branches. So the total current equals 0.5 plus 1 plus 1, which equals 2.5 amps. Step 6. The series 5-ohm resistor. It carries the full 2.5 amps. Its voltage drop is V equals I times R equals 2.5 times 5, which equals 12.5 volts. Step 7. KVL around the outer loop. Starting at the source and going around. Vx must equal the drop across the series 5-ohm resistor plus the voltage across the parallel network. So Vx equals 12.5 plus 5, which equals 17.5 volts. Therefore, Vx equals 17.5 volts. Alternative check. The 3 parallel resistors, 10, 5, and 5, combine to 1 over 10 plus 1 over 5 plus 1 over 5 equals 0.1 plus 0.2 plus 0.2 equals 0.5 Siemens. So the parallel equivalent is 2 ohms. Total resistance from the source is 5 plus 2, which is 7 ohms. Total current is 2.5 amps. So Vx equals 2.5 times 7, which equals 17.5 volts. Same answer, arrived at from the other direction. When 2 independent methods agree, you are done. The general lesson from problem 2. When a problem gives you a current or voltage deep inside the network rather than the source value, do not try to write equations from the source. Start at the given quantity and propagate outward using Ohm's law, KCL at every junction, and KVL along every path, until you reach the source. Chapter 4. Nodal Analysis, Supernodes, and Practice Pocket Problem 3. Nodal analysis is the workhorse method for any circuit that series parallel reduction cannot crack. It is built on Kirchhoff's current law and the unknowns you solve for our node voltages. Here is the procedure, and I want you to memorize it as a fixed sequence of steps, because on an exam the biggest risk is not the algebra, it is skipping a step. Step 1. Count the nodes. Remember, a node is an entire connected stretch of wire. If you have n nodes total, you will end up with n-1 equations. Step 2. Pick a reference node and call it ground. Its voltage is defined as 0. Choose wisely. The best choice is usually the node with the most branches attached, or the node at the bottom of the circuit, or, if there is a voltage source with one terminal connected to a big common wire, put ground at that terminal, because then the other terminal of that source is a known voltage and you have eliminated an unknown for free. Step 3. Label every remaining node with an unknown voltage, V1, V2, V3, and so on. These are voltages measured with respect to ground. Step 4. At each non-reference node, write KCL, sum the currents leaving the node, and set the sum equal to 0, or set it equal to the current pushed in by any current sources. Step 5. Express every resistor current in terms of node voltages using Ohm's law. Step 6. Solve the system. Now, Step 5 is where the real technique lives, so let us slow down. The current leaving node A through a resistor are toward node B equals VA minus VB, all divided by R. Say that out loud, because it is the single most important pattern in nodal analysis. The voltage at the node you are standing on, minus the voltage at the node on the other side, divided by the resistance in between. Here, minus there, over R. If the other side is ground, then VB is 0, and the term simplifies to just VA over R. If you write every term as leaving the node, then every term has the form this node minus the other node, and the signs take care of themselves. Adopt the convention that everything leaves the node and never change it. That consistency is what protects you from sign errors. Current sources are handled by moving them to the right-hand side. If a current source pushes current into the node, it appears on the right-hand side as a positive number. If it draws current out of the node, it appears as a negative number or as a positive term on the left. Whichever convention you use, be consistent. The remaining complication is voltage sources, because a voltage source does not have a nice current versus voltage relationship you can write down. Ohm's law does not apply to it. There are 3 cases. Case 1. The voltage source has one terminal connected to ground. Then the other terminal is at a known voltage, equal to plus or minus the source value. That node is no longer an unknown. Just write its value directly and skip writing KCL for it. This is the easy case, and it is why choosing ground next to a source is smart. Case 2. The voltage source sits between 2 non-reference nodes. Now neither node voltage is known individually, but their difference is known. This is the supernode case, and we will do it in detail in a moment. Case 3. There is a dependent voltage source. Handle it like case 1 or 2, then add the extra controlling equation. Let us define the supernode properly. A supernode is formed by enclosing a voltage source and the 2 nodes at its ends inside a single imaginary bubble. You then apply KCL to the entire bubble. All the current entering the bubble must equal all the current leaving it. Currents that flow through the source itself are internal to the bubble and never appear in the equation, which is exactly the point, because you do not know that current. A supernode gives you one KCL equation covering 2 nodes. But you have 2 unknowns. So you need one more equation, and that is the constraint equation, which comes straight from the source itself. V of the plus terminal minus V of the minus terminal equals the source value. So the recipe is 1 KCL around the bubble plus 1 constraint equation. 2 equations, 2 unknowns, balance restored. Now let us do practice pocket problem 3 with this machinery. The setup. There are 4 labeled nodes, V1, V2, V3, and V4, plus a ground at the bottom. Here are the connections. A 4 kΩ resistor runs from node V2 to node V1. A 10-volt source sits directly between node V1 and node V4, with its positive terminal on the V1 side. A 1 kΩ resistor runs from node V1 down to node V3. A 3 kΩ resistor runs from node V2 to node V3. A 2 kΩ resistor runs from node V3 to node V4. A 2 kΩ resistor runs from node V2 down to ground. A 5 kΩ resistor runs from node V4 down to ground. And a 2 milliamp current source pushes current upward from ground into node V3. Now, before writing anything, notice the unit trick. Every resistor is in kiloohms, every source is in volts. The current source is in milliamps. So we can drop all the prefixes, use bare numbers, and our answers will come out in volts and milliamps automatically. Also notice, the 10-volt source connects V1 and V4, and neither of them is ground. So that is a supernode. Immediately write the constraint. Constraint equation. V1 minus V4 equals 10. Since the plus terminal is on the V1 side, V1 is 10 volts above V4. Now node V2. It is a plain node with no voltage source attached. So we just write KCL, everything leaving. Leaving V2 through the 4 kΩ resistor toward V1. V2 minus V1 over 4. Leaving V2 through the 3 kΩ resistor toward V3. V2 minus V3 over 3. Leaving V2 through the 2 kΩ resistor toward ground. v2 minus 0 over 2, which is just v2 over 2. Set the sum to 0. So, v2 minus v1 over 4 plus v2 minus v3 over 3 plus v2 over 2 equals 0. Clear the fractions. The least common multiple of 4, 3, and 2 is 12. Multiply every term by 12. 12 over 4 is 3, so the first term becomes 3 times the quantity v2 minus v1. 12 over 3 is 4, so the second term becomes 4 times the quantity v2 minus v3. 12 over 2 is 6, so the third term becomes 6v2. That gives 3v2 minus 3v1 plus 4v2 minus 4v3 plus 6v2 equals 0. Collect the v1 terms, negative 3v1. The v2 terms, 3 plus 4 plus 6 is 13, so 13v2. The v3 terms, negative 4v3. Equation 1. Negative 3v1 plus 13v2 minus 4v3 equals 0. Now, node v3. It has the current source attached, pushing 2 milliamps in, leaving v3 toward v1 through the 1 kilo ohm resistor. v3 minus v1 over 1, which is just v3 minus v1. Leaving v3 toward v2 through the 3 kilo ohm resistor. v3 minus v2 over 3. Leaving v3 toward v4 through the 2 kilo ohm resistor. v3 minus v4 over 2. The sum of currents leaving equals the current injected by the source, which is 2 milliamps. So, v3 minus v1 plus v3 minus v2 over 3 plus v3 minus v4 over 2 equals 2. Clear fractions by multiplying by 6. 6 times the quantity v3 minus v1 plus 2 times the quantity v3 minus v2 plus 3 times the quantity v3 minus v4 equals 12. Expand and collect. v1 terms, negative 6v1. v2 terms, negative 2v2. v3 terms, 6 plus 2 plus 3 is 11, so 11v3. v4 terms, negative 3v4. Equation 2. Negative 6v1 minus 2v2 plus 11v3 minus 3v4 equals 12. Now the supernode containing v1 and v4. Draw the bubble around the 10-volt source and both of its nodes. Now list every branch that crosses the bubble boundary. From v1 out through the 4 kilo ohm resistor toward v2, v1 minus v2 over 4. From v1 out through the 1 kilo ohm resistor toward v3, v1 minus v3 over 1. From v4 out through the 2 kilo ohm resistor toward v3, v4 minus v3 over 2. From v4 out through the 5 kilo ohm resistor toward ground, v4 over 5. Those 4 branches are the only ways current can cross the bubble. The current through the 10-volt source itself stays inside the bubble and never appears. Set the sum to 0. v1 minus v2 over 4 plus v1 minus v3 plus v4 minus v3 over 2 plus v4 over 5 equals 0. Clear fractions. Least common multiple of 4, 1, 2, and 5 is 20. Multiply everything by 20. 5 times the quantity v1 minus v2 plus 20 times the quantity v1 minus v3 plus 10 times the quantity v4 minus v3 plus 4v4 equals 0. Expand and collect. v1 terms. 5 plus 20 is 25, so 25v1. v2 terms. Negative 5v2. v3 terms. Negative 20 minus 10 is negative 30, so negative 30v3. v4 terms. 10 plus 4 is 14, so 14v4. Equation 3. 25v1 minus 5v2 minus 30v3 plus 14v4 equals 0. And equation 4 is the constraint. v1 minus v4 equals 10. For equations, for unknowns. Let me read them back so you have them. 1. Negative 3v1 plus 13v2 minus 4v3 equals 0. 2. Negative 6v1 minus 2v2 plus 11v3 minus 3v4 equals 12. 3. 25v1 minus 5v2 minus 30v3 plus 14v4 equals 0. 4. v1 minus v4 equals 10. Solving that system gives the following. V1 equals 384 over 41, which is 9.37 volts. V2 equals 872 over 205, which is 4.25 volts. V3 equals 34 over 5, which is exactly 6.8 volts. V4 equals negative 26 over 41, which is negative 0.634 volts. Notice V4 is negative. That is completely legitimate. It simply means node 4 sits below ground potential. Never assume a node voltage must be positive. And check the constraint. 9.37 minus negative 0.634 equals 10.0. Correct. If you want to verify equation 1 quickly, negative 3 times 9.37 is negative 28.1. 13 times 4.25 is 55.3. Negative 4 times 6.8 is negative 27.2. Add them. Negative 28.1 plus 55.3 is 27.2, minus 27.2 is 0. Equation 1 satisfied. Let me give you the practical strategy points for nodal analysis on the exam. First, choosing ground at the bottom rail where the current source returns is almost always correct. Second, count your equations before you solve. Number of non-reference nodes equals number of equations. A supernode absorbs 2 nodes, but produces 1 KCl plus 1 constraint, so the count still works out. Third, always multiply through to clear denominators before solving. Fractions cause arithmetic mistakes under time pressure. Fourth, when should you choose nodal over mesh? Count. If the circuit has fewer nodes than meshes, use nodal. If it has fewer meshes than nodes, use mesh. Also, if the circuit is dominated by current sources, nodal is easier because current sources drop straight into the right-hand side with no extra work. If it is dominated by voltage sources, mesh is usually easier for the mirror image reason. Fifth, if a problem asks only for one specific voltage or current, consider whether Thevenin, superposition, or source transformation would get there faster than a full node solve. On a timed exam, method selection is worth as much as algebra skill. Chapter 5. Mesh Analysis, Supermeshes, and Practice Pocket Problem 4. Mesh analysis is the mirror image of nodal analysis. It is built on Kirchhoff's voltage law, and the unknowns you solve for are mesh currents. A mesh current is a fictitious current that you imagine circulating around a single window pane of the circuit. It is a bookkeeping device. The actual physical current in any branch is the algebraic combination of the mesh currents that flow through that branch. Here is the procedure. Step 1. Make sure the circuit is planar, meaning it can be drawn with no wires crossing. Mesh analysis only works on planar circuits. Almost everything you will see in this class is planar. Step 2. Identify the meshes, the window panes. Assign a mesh current to each one, and, this is important, assign them all in the same direction. Universally, we choose clockwise. Every mesh current clockwise, every time. If you do that, the equations take a predictable form and the sign errors mostly disappear. Step 3. Apply KVL around each mesh, going around in the same direction as the mesh current. Step 4. Express each resistor voltage using Ohm's law in terms of mesh currents. Step 5. Solve. The critical technique is in step 4, so let us be precise. For a resistor that belongs to only one mesh, the voltage drop as you travel around in the direction of the mesh current is simply R times that mesh current, and it is a drop, so it enters KVL with a positive sign if you are summing drops. For a resistor shared between 2 adjacent meshes, the current through it, in the direction of mesh 1, is mesh current 1 minus mesh current 2. Because the 2 mesh currents flow through that shared element in opposite physical directions. So the voltage drop, as seen from mesh 1, is R times the quantity I1 minus I2. Say it out loud. Shared resistor. My mesh current minus the neighbor's mesh current, times R. Voltage sources are easy in mesh analysis, which is the whole reason to prefer mesh when a circuit is full of voltage sources. As you travel around the loop, if you go from the minus terminal to the plus terminal, that is a voltage rise, so it enters as a negative drop. If you go from plus to minus, that is a drop, positive. The complication in mesh analysis is current sources, because a current source does not have a defined voltage across it. Again, 3 cases. Case 1. The current source belongs to only one mesh, sitting on the outer boundary. Then that mesh current is simply known. It equals the source value, with a sign depending on whether the source arrow agrees with your clockwise mesh direction. You do not write a KVL equation for that mesh at all. You just write down the answer. That eliminates an unknown for free. Case 2. The current source is shared between two meshes. Now neither mesh current is known individually, but their difference is known. This is the supermesh case. Case 3. Dependent current source. Handle as above, then add a controlling equation. The supermesh. Here is the definition and the procedure. A supermesh is formed when two meshes share a branch containing a current source. You mentally remove the current source branch, and then write one KVL equation around the outer perimeter of the combined region formed by both meshes. Because you avoided walking through the current source, you never need to know the voltage across it, which is exactly the point. Then you add one constraint equation from the current source itself. The difference of the two mesh currents equals the source value. Getting the sign of that constraint right requires you to check the arrow direction against your mesh current directions. One KVL around the outside, plus one constraint. Two equations, two unknowns. Same balance as the supernode. Now, practice pocket problem 4. The setup. Picture three meshes. Across the very top, there is a 12.5 amp current source with its arrow pointing to the right. That current source is the only element in the top mesh besides wires. On the left side, going down, there is a 1 ohm resistor, and below it a 100-volt source with its positive terminal on top. Horizontally, in the middle there is a 2 ohm resistor. Hanging down in the middle from the middle node there is a 4 ohm resistor, and the output voltage V0 is defined across that 4 ohm resistor, positive at the top. On the upper right, there is an 8 ohm resistor, and on the right side a 50-volt source. Define three clockwise mesh currents. I1 is the top mesh. I2 is the lower left mesh. I3 is the lower right mesh. Step 1. The 12.5 amp current source is in the top mesh only. So mesh 1 is known immediately. I1 equals 12.5 amps. Done. No equation needed for mesh 1. Step 2. KVL around the lower left mesh, mesh 2. The elements in mesh 2 are the 2 ohm resistor, shared with mesh 1. The 4 ohm resistor, shared with mesh 3. The 1 ohm resistor, belonging only to mesh 2. And the 100-volt source. Write the sum of drops equals 0. Drop across the 2 ohm resistor from mesh 2's viewpoint. 2 times the quantity I2 minus I1. Drop across the 4 ohm resistor, shared with mesh 3. 4 times the quantity I2 minus I3. Drop across the 1 ohm resistor. 1 times I2, which we just write as I2. The 100-volt source. Traveling around clockwise we go from plus to minus in a way that represents a rise, so it enters as minus 100. Putting it together, 2 times the quantity I2 minus I1, plus 4 times the quantity I2 minus I3, plus I2, minus 100, equals 0. Substitute I1 equals 12.5. 2 times the quantity I2 minus 12.5, plus 4 times the quantity I2 minus I3, plus I2, minus 100, equals 0. Expand. 2I2 minus 25, plus 4I2 minus 4I3, plus I2, minus 100, equals 0. Collect. I2 terms. 2 plus 4 plus 1 is 7, so 7I2. I3 terms. Negative 4I3. Constants. Negative 25 minus 100 is negative 125. So 7I2 minus 4I3 minus 125 equals 0, which rearranges to equation A. 7I2 minus 4I3 equals 125. Step 3. KVL around the lower right mesh, mesh 3. The elements are the 8 ohm resistor, the 4 ohm resistor shared with mesh 2, and the 50-volt source. Drop across the 8 ohm resistor, 8I3. Drop across the 4 ohm resistor from mesh 3's viewpoint. 4 times the quantity I3 minus I2. The 50-volt source, it enters as minus 50, given its orientation. So 8I3 plus 4 times the quantity I3 minus I2 minus 50 equals 0. Expand. 8I3 plus 4I3 minus 4I2 minus 50 equals 0. Collect. 12I3 minus 4I2 equals 50. Equation B. Negative 4i2 plus 12i3 equals 50. Step 4. Solve the pair. Equation A. 7i2 minus 4i3 equals 125. Equation B. Negative 4i2 plus 12i3 equals 50. Multiply equation A by 3. 21i2 minus 12i3 equals 375. Now add equation B. Negative 4i2 plus 12i3 equals 50. The i3 terms cancel. 21 minus 4 is 17. So 17i2 equals 425. Therefore, I2 equals 25 amps. Substitute back into equation B. Negative 4 times 25 is negative 100. So negative 100 plus 12i3 equals 50, which means 12i3 equals 150. So I3 equals 12.5 amps. So I1 is 12.5, I2 is 25, and I3 is 12.5 amps. Step 5. Get V0. The 4-ohm resistor is shared between meshes 2 and 3. The current through it, flowing downward, is I2 minus I3, which is 25 minus 12.5, which equals 12.5 amps. Since V0 is defined positive at the top of the 4-ohm resistor, and the current flows downward through it, Ohm's law gives V0 equals 4 times 12.5, which equals 50 volts. V0 equals 50 volts. Notice something elegant. The current through the 4-ohm resistor happens to be 12.5 amps, exactly equal to the source current, and V0 comes out to a clean 50 volts. Exam problems are usually engineered to have clean answers. If your answer to a mesh problem is something like 49.372, double-check your arithmetic. Not always wrong, but worth a second look. Now a few strategic notes on mesh analysis. First, always go clockwise. Always. The moment you mix directions, the shared resistor terms change sign and you will lose track. Second, when the sum of drops formulation confuses you, use the alternative phrasing. Sum of voltage rises equals sum of voltage drops. Both work. Pick one and never switch mid-problem. Third, count meshes versus nodes before you commit. Problem 4 has 3 meshes and, if you count them, 4 or 5 nodes. 3 equations beats 4, and one of the 3 equations was free because of the current source. Mesh was clearly the right call here, which is why the problem said use mesh analysis. Fourth, the number of mesh equations equals the number of meshes, minus 1 for every current source that sits alone in a single mesh, because each of those gives you a mesh current for free. Fifth, once you have all the mesh currents, you can get any branch current in the circuit by combining them, and then any voltage by Ohm's law. Do not stop at the mesh currents. Read the question again and make sure you have answered what was actually asked. Students routinely solve for all 3 mesh currents perfectly and then forget to compute the requested output voltage. Chapter 6. Practice Pocket Problem 5, the supermesh, and Thevenin and Norton equivalents. Problem 5 is the richest problem in the pocket because it combines a supermesh with a Thevenin equivalent. Let us set it up carefully. The setup: along the top, from left to right, a 90-ohm resistor, then a second 90-ohm resistor, then we reach terminal A. On the far left, connecting the top rail to the bottom rail, is a 180-volt source with its positive terminal on top. In the middle, connecting the top rail to the bottom rail, is a 2-amp current source with its arrow pointing upward. Then, between the 2 90-ohm resistors and terminal A, hanging from the top rail down to the bottom rail, is a 60-ohm resistor. And to the right of terminal A, a 15-ohm resistor connects down to terminal B on the bottom rail. The current I flows downward through the 15-ohm resistor. Define 3 clockwise mesh currents. I1 is the left mesh, bounded by the 180-volt source, the first 90-ohm resistor, and the current source branch. I2 is the middle mesh, bounded by the current source branch, the second 90-ohm resistor, and the 60-ohm resistor. I3 is the right mesh, bounded by the 60-ohm resistor and the 15-ohm resistor. The 15-ohm resistor is the load, and it belongs only to mesh 3. So the answer we eventually want, the current I, equals I3. Part A. Mesh analysis. The 2-amp current source sits in the branch shared between mesh 1 and mesh 2. That means we cannot write ordinary KVL for either of those meshes, because we do not know the voltage across a current source. So we form a supermesh. First, the constraint. In the shared branch, mesh current I2 flows upward and mesh current I1 flows downward. because they are both clockwise but on opposite sides of that branch. The source pushes 2 amps upward. Therefore, I2 minus I1 equals 2 amps. That is the constraint equation. Second, the supermesh KVL walk around the outer boundary of meshes 1 and 2 combined, skipping the current source branch entirely. Starting at the bottom left and going clockwise, we rise through the 180-volt source, so that contributes negative 180. Then we drop across the first 90-ohm resistor, contributing 90 I1. Then we cross the top and drop across the second 90-ohm resistor, contributing 90 I2. Then we come down through the 60-ohm resistor, which is shared with mesh 3, contributing 60 times the quantity, I2 minus I3. Then we return along the bottom, setting the sum to 0, negative 180, plus 90 I1, plus 90 I2, plus 60 times the quantity, I2 minus I3, equals 0. Expand and rearrange. 90 I1, plus 90 I2, plus 60 I2, minus 60 I3, equals 180. Collect the I2 terms. 90 plus 60 is 150. Supermesh equation. 90 I1, plus 150 I2, minus 60 I3, equals 180. Third, mesh 3. It is an ordinary mesh, no current source, so plain KVL. Drop across the 15-ohm resistor, 15 I3. Drop across the 60-ohm resistor from mesh 3's viewpoint. 60 times the quantity, I3 minus I2. There are no sources in this mesh. So 15 I3 plus 60 times the quantity, I3 minus I2, equals 0. Expand. 15 I3 plus 60, I3 minus 60, I2 equals 0, which gives 75 I3 minus 60, I2 equals 0. Therefore, I3 equals 60 over 75 times I2, which is 0.8 times I2. Now substitute. From the constraint, I1 equals I2 minus 2. From mesh 3, I3 equals 0.8 I2. Put both into the supermesh equation. 90 times the quantity, I2 minus 2, plus 150 I2, minus 60 times 0.8 I2, equals 180. Expand. 90 I2 minus 180, plus 150 I2, minus 48 I2, equals 180. Collect the I2 terms. 90 plus 150 is 240, minus 48 is 192. So 192 I2 minus 180 equals 180, which gives 192 I2 equals 360. Therefore, I2 equals 360 over 192, which equals 1.875 amps. Then I1 equals 1.875 minus 2, which equals negative 0.125 amps. Negative. That is fine. It simply means the actual current in mesh 1 circulates counterclockwise, opposite to the direction we assumed. You do not go back and fix the diagram. You keep the negative sign and carry it through. And I3 equals 0.8 times 1.875, which equals 1.5 amps. So the load current I3 equals 1.5 amps, flowing downward through the 15-ohm resistor. Now the voltages across each resistor. The left 90-ohm resistor carries I1, whose magnitude is 0.125 amps. Its voltage magnitude is 0.125 times 90, which equals 11.25 volts. Remember, the actual current direction through it is opposite to the assumed clockwise direction. The right 90-ohm resistor carries I2, which is 1.875 amps. Its voltage is 1.875 times 90, which equals 168.75 volts. That is a big drop, and it should be, because that resistor is carrying almost 2 amps. The 60-ohm resistor is shared between meshes 2 and 3, so its current is I2 minus I3, which is 1.875 minus 1.5, which equals 0.375 amps. Its voltage is 0.375 times 60, which equals 22.5 volts. The 15-ohm resistor carries I3, which is 1.5 amps. Its voltage is 1.5 times 15, which equals 22.5 volts. And notice, both come out to 22.5 volts. That is not a coincidence. The 60-ohm and the 15-ohm resistors are both connected between terminal A and terminal B. They are in parallel. Parallel elements must have the same voltage. That agreement is a strong confirmation that our whole solution is correct. Now, part B, the Thevenin equivalent. And before we do it for this circuit, let us establish the theory properly, because Thevenin is guaranteed exam material. Thevenin's theorem says this: any linear two-terminal network, no matter how complicated inside, can be replaced, as seen from those two terminals, by a single voltage source V Thevenin in series with a single resistance, R Thevenin. From the outside, no measurement you can make at those terminals can tell the difference. Norton's theorem is the dual. Any linear two-terminal network can be replaced by a single current source I Norton in parallel with a single resistance R Norton. The two are related by a source transformation. V Thevenin equals I Norton times R, and R Thevenin equals R Norton. Same resistance in both. If you find one, you have essentially found the other. How do you find V Thevenin? Remove the load, leaving the terminals open, and compute the open circuit voltage across those terminals. That open circuit voltage is V Thevenin. This is why V Thevenin is also called V open circuit. How do you find I Norton? Replace the load with a short circuit and compute the current that flows through that short. That is I Norton, also called I short circuit. How do you find R Thevenin? There are three methods, and you should know all three because different problems call for different ones. Method 1, and the easiest when it applies. Deactivate all independent sources and compute the equivalent resistance looking back into the terminals. Deactivating means replace every independent voltage source with a short circuit because an ideal voltage source with 0 volts is a wire, and replace every independent current source with an open circuit because an ideal current source with 0 amps is a break. Then just do series parallel reduction from the terminals inward. Warning: this method only works if the circuit contains no dependent sources. Method 2, and this always works. Compute both the open circuit voltage and the short circuit current, and then R Thevenin equals V open circuit divided by I short circuit. This works even with dependent sources. Method 3, the test source method, for circuits that contain dependent sources but no independent sources. Deactivate the independent sources, apply a 1-volt test source across the terminals, compute the resulting current, and R Thevenin equals 1 volt divided by that current. Or apply a 1 amp test current and measure the voltage. Either way, now let us apply Thevenin to problem 5, looking back from terminals A and B with the 15 ohm load removed. Step 1. Find V Thevenin, the open circuit voltage. Remove the 15 ohm resistor. Now mesh 3 is gone entirely, so I3 equals 0. Redo the supermesh with I3 equal to 0. The equation becomes 90 I1 plus 150 I2 equals 180. And the constraint is still I1 equals I2 minus 2. Substitute 90 times the quantity I2 minus 2 plus 150 I2 equals 180. That is 90 I2 minus 180 plus 150 I2 equals 180. Collecting 240 I2 equals 360, so I2 equals 1.5 amps. With the load removed, all of I2 flows down through the 60 ohm resistor. So the open circuit voltage across terminals A and B is 60 times 1.5, which equals 90 volts. V Thevenin equals 90 volts. Step 2. Find R Thevenin. There are no dependent sources here, so use method 1. Deactivate the sources. The 180 volt source becomes a short circuit. The 2 amp current source becomes an open circuit. Now look back into terminals A and B. With the current source opened, the middle vertical branch is gone. So from terminal A, one path goes up and left through the second 90 ohm resistor, then continues left through the first 90 ohm resistor, and then reaches the shorted 180 volt source, which drops us straight down to the bottom rail, which is terminal B. That path is 90 plus 90, which is 180 ohms. The other path from terminal A is straight down through the 60 ohm resistor to terminal B. Those two paths are in parallel. R Thevenin equals 180 times 60 divided by 180 plus 60. The numerator is 10,800. The denominator is 240. Divide, and you get 45 ohms. R Thevenin equals 45 ohms. Step 3. Verify. Reattach the 15 ohm load to the Thevenin equivalent. The current through it is V Thevenin divided by the sum of R Thevenin and the load. That is 90 divided by 45 plus 15, which is 90 divided by 60, which equals 1.5 amps. And 1.5 amps is exactly the load current we found by mesh analysis. The Thevenin equivalent is verified. The Norton equivalent, for completeness. I Norton equals V Thevenin over R Thevenin, which is 90 over 45, which equals 2 amps. So the Norton equivalent is a 2 amp current source in parallel with a 45 ohm resistor. And now the payoff question that exams love. Maximum power transfer. The maximum power transfer theorem states that a source network delivers maximum power to a load when the load resistance equals the Thevenin resistance of the source network. Our load equals our Thevenin. For this circuit, maximum power is delivered when the load is 45 ohms, not 15. And the maximum power itself is given by P max equals V Thevenin squared, divided by 4 times our Thevenin. That formula comes from splitting the voltage evenly between two equal resistances, so the load sees half the Thevenin voltage, and then computing V over 2 squared divided by R. For our circuit, 90 squared is 8,100. For times 45 is 180. 8,100 divided by 180 equals 45 watts. So the maximum power this network can deliver to any load is 45 watts, achieved with a 45 ohm load. For comparison, the actual 15 ohm load receives I squared R, which is 1.5 squared times 15, which is 2.25 times 15, which is 33.75 watts. Less than 45, as it must be. One more crucial point about maximum power transfer. At the match condition, the efficiency is only 50% because the Thevenin resistance dissipates exactly as much power as the load. That is acceptable in signal and communication systems, where you care about extracting maximum signal power. It is completely unacceptable in power systems, where you care about efficiency and you deliberately want the source resistance to be much smaller than the load. Exam questions sometimes ask about that distinction conceptually, so know it. Let me summarize the Thevenin procedure as a chant you can repeat while driving. Remove the load. Find the open circuit voltage, that is V Thevenin. Kill the independent sources, voltage sources become shorts, current sources become opens. Find the resistance looking in, that is our Thevenin. Put the load back on the simple series circuit. Solve. And if there are dependent sources, do not kill anything. Instead find both V open circuit and I short circuit and divide. Chapter 7. Source Transformation, Practice Pocket Problem 6, Superposition and Linearity. Source transformation is the fastest circuit simplification tool you own, and it is criminally underused by students on exams. The idea. A voltage source Vs in series with a resistance Rs is completely equivalent, as seen from its two terminals, to a current source Is in parallel with the same resistance Rs, provided that Is equals Vs divided by Rs. And it works in reverse. A current source Is in parallel with Rs is equivalent to a voltage source of value Is times Rs in series with Rs. The resistance value never changes. Only the source type and value change. Now the part everyone gets wrong, the direction. Going from a voltage source to a current source, the current source arrow must point toward the terminal that was the positive terminal of the voltage source. Think of it physically. The voltage source pushes conventional current out of its positive terminal into the external circuit. The equivalent current source must push current the same way. So the arrow points toward the plus side. Going from a current source to a voltage source, the positive terminal of the new voltage source goes on the side the arrow was pointing toward. Say it out loud. The arrow points to the plus. Two absolutely critical restrictions. First, the resistance must actually be in series with the voltage source, or actually in parallel with the current source. If there is a node in between where another branch taps off, the transformation is not valid. Second, and this is the subtle one, the transformation is only equivalent at the external terminals. The internal currents and voltages of the transformed piece are not the same. So if the problem asks for the current through that specific 90 ohm resistor, and you transformed it away, you cannot read the answer off the transformed circuit. You have to go back to the original. Source transformation is for finding things outside the transformed section. Also note the two degenerate cases. An ideal voltage source with no series resistance cannot be transformed. Neither can an ideal current source with no parallel resistance. There is nothing to transform. Now, Practice pocket problem 6. The setup is the same circuit as problem 5. On the left, a 180-volt source in series with a 90-ohm resistor. In the middle, a 2-amp current source pointing upward. Then a second 90-ohm resistor, then a 60-ohm resistor down to the bottom rail, then a 15-ohm load. The task is to use source transformation to unify the two independent sources into one. Step 1. Look at the left branch. We have a 180-volt source in series with 90 ohms. That is a Thevenin form, and it can become a Norton form. The equivalent current is IS equals Vs divided by Rs, which is 180 divided by 90, which equals 2 amps. The positive terminal of the 180-volt source is at the top, so the equivalent current source points upward from the bottom rail toward the upper node. Therefore, 180 volts in series with 90 ohms becomes 2 amps in parallel with 90 ohms. That is the answer the practice pocket asks for. But let us keep going, because the exam will almost certainly ask you to finish the job, and this is where source transformation really shines. Step 2. Combine the sources. After the transformation, we now have, connected between the upper middle node and the bottom rail, a 2-amp source pointing upward, in parallel with a 90-ohm resistor, and right next to it the original 2-amp source also pointing upward. Two current sources in parallel, both pointing the same direction, simply add. So we now have a single 4-amp source pointing upward, in parallel with that same 90-ohm resistor. The two independent sources have been unified into one. That was the goal. Step 3. Transform back, to make the rest trivial. A 4-amp source in parallel with 90 ohms becomes a voltage source of 4 times 90, which equals 360 volts, in series with 90 ohms, with the positive terminal at the top, since the arrow pointed up. Step 4. Now the circuit is a simple series chain. 360 volts, in series with 90 ohms, in series with the second 90-ohm resistor, feeding the 60-ohm resistor in parallel with the 15-ohm load. The two 90-ohm resistors are now genuinely in series, so they combine to 180 ohms. The 60 and the 15 in parallel. Product over sum is 60 times 15, which is 900, over 75, which equals 12 ohms. Total resistance is 180 plus 12, which is 192 ohms. Total current is 360 divided by 192, which equals 1.875 amps. And look at that, 1.875 amps. That is exactly I2 from the mesh analysis in problem 5. The methods agree. The voltage across the parallel section is 1.875 times 12, which equals 22.5 volts. Again, matching our earlier result exactly. And the load current is 22.5 divided by 15, which equals 1.5 amps. Matching again. That is the power of source transformation. What took a supermesh, a constraint equation, and a 3x3 system in problem 5 took 4 transformations and 1 division here. Notice also how easily this gives the Thevenin equivalent. With the load removed, the open circuit voltage is a simple voltage divider, 360 times 60 over the quantity 180 plus 60, which is 360 times 60 over 240, which equals 90 volts. That is V Thevenin, matching chapter 6. And killing the 360-volt source shorts it, leaving 180 in parallel with 60, which is 45 ohms. That is our Thevenin, also matching. Source transformation is often the fastest route to a Thevenin equivalent. Now let us cover superposition, which is the other great linear circuit technique. The superposition principle states that in a linear circuit with multiple independent sources, the voltage or current at any point equals the algebraic sum of the contributions from each independent source acting alone, with all other independent sources deactivated. Deactivated means, again, voltage sources become short circuits, current sources become open circuits. Critical rules for superposition. 1. You never deactivate dependent sources. Dependent sources stay active in every single subcircuit because their value depends on the circuit conditions, not on an external supply. Only independent sources get turned off one at a time. 2. Superposition applies to voltage and current, which are linear quantities. It does not apply to power, because power involves a square. If source 1 alone gives 2 amps through a resistor and source 2 alone gives 3 amps, the total current is 5 amps. and the power is 25 times R, not 4 or plus 9R. Do not superpose power. Exams test this exact misconception. 3. Superposition is usually more work than nodal or mesh analysis, so it is not your default method. Use it when a problem explicitly asks for it, when you want to understand the individual contribution of one source, or when the sources are of very different types and one subcircuit collapses to something trivial. Here is the procedure. Turn off all sources except one. Solve for the quantity of interest and label the result with a subscript. Repeat for each source. Add all the results algebraically, watching signs carefully, because contributions can oppose each other. Let us do a quick worked superposition example so it sticks. Suppose we have a 12-volt source in series with a 4-ohm resistor connected to a node, and from that node an 8-ohm resistor goes to ground, and a 3-amp current source also pushes current into that node from ground. Find the node voltage. Contribution 1. The 12-volt source acting alone. Turn off the current source, which means open it. Now we have a simple voltage divider. 12 volts across 4 ohms in series with 8 ohms. The node voltage is 12 times 8 over 12, which equals 8 volts. Contribution 2. The 3-amp source acting alone. Turn off the voltage source, which means short it. Now the 4-ohm resistor runs from the node to ground, and the 8-ohm resistor also runs from the node to ground. They are in parallel, giving 4 times 8 over 12, which equals 2.667 ohms. The 3-amp source pushes 3 amps through that, so the node voltage is 3 times 2.667, which equals 8 volts. Total node voltage, 8 plus 8 equals 16 volts. Now verify with nodal analysis on the original circuit. KCL at the node, V minus 12 over 4 plus V over 8 equals 3. Multiply by 8. 2 times the quantity V minus 12 plus V equals 24. That is 2V minus 24 plus V equals 24, so 3V equals 48, so V equals 16 volts. Confirmed. Now, linearity itself, since superposition depends on it. A circuit is linear if it satisfies two properties. Homogeneity, also called scaling. If you multiply the input by a constant K, the output is multiplied by the same constant K. And additivity. The response to a sum of inputs is the sum of the responses. Resistors, capacitors, inductors, ideal op-amps in their linear region, and dependent sources with constant coefficients are all linear elements. Diodes and transistors are not linear. Linearity gives you a nice exam shortcut. If a problem says the source is 20 volts and the output is 3 volts, and then asks what the output would be if the source were 50 volts, you do not resolve anything. You scale. 50 over 20 is 2.5, so the output is 2.5 times 3, which is 7.5 volts. That works only when the circuit has a single independent source, or when you scale all sources together. There is also a related trick called the assumption method, or the ladder method, for pure resistive ladders driven by a single source. You assume the output is 1 amp or 1 volt. Work backwards to find what source that would require. Then scale everything by the ratio of the real source to the assumed source. Problem 2 in your pocket was essentially this method, done forwards. To close the chapter, here is your method selection guide, which is worth as much as any formula. If the circuit reduces by series and parallel, just reduce it. Fastest. If you need one branch quantity and the rest is complicated, use Thevenin. If sources are mixed types and one branch is isolated, use source transformation. If the circuit has many voltage sources and few meshes, use mesh. If the circuit has many current sources and few nodes, use nodal. If the problem explicitly names a method, use that method, because they are grading the method, not just the number. Chapter 8. Operational Amplifiers, and Practice Pocket Problems 8 and 9. The operational amplifier, or op-amp, is a 5-terminal device drawn as a triangle. 2 inputs on the left, 1 output on the right, and 2 power supply terminals, positive and negative, that are usually not drawn but are always physically there. The 2 inputs are the inverting input, marked with a minus sign, and the non-inverting input, marked with a plus sign. Do not confuse those plus and minus marks with polarity of a voltage source. They label which input is which. The op-amp amplifies the difference between its 2 inputs. The output equals the open loop gain, capital A, times the quantity V plus minus V minus. For a real op-amp, A is enormous, typically 100,000 to 1 million. For an ideal op-amp, A is infinite. The ideal op-amp model rests on 3 assumptions, and you should be able to recite them. Assumption 1. The open-loop gain is infinite. Assumption 2. The input resistance is infinite, which means no current flows into either input terminal. Assumption 3. The output resistance is 0, which means the output can supply any current at whatever voltage it wants, and its voltage does not sag under load. From these come the 2 golden rules that you will actually use to solve every op-amp problem. Golden Rule 1. No current flows into either input terminal. The current into the plus input is 0 and the current into the minus input is 0. Golden Rule 2. When there is negative feedback, meaning a path from the output back to the inverting input, the voltage at the plus input equals the voltage at the minus input. V plus equals V minus. Rule 2 is called the virtual short, and here is the reasoning. The output equals A times the input difference. If A is infinite and the output is finite, then the input difference must be 0. The feedback path is what forces the output to settle at whatever value makes the difference 0. If the inverting input is connected through the feedback network and the non-inverting input is grounded, then the inverting input sits at 0 volts. We call that a virtual ground. It is at ground potential, but it is not physically connected to ground, and no current flows into it. 2 warnings. Rule 2 only holds with negative feedback. If the feedback goes to the plus input instead, that is positive feedback and you get a comparator or a Schmitt trigger, not a linear amplifier, and the golden rules do not apply. And second, the output can never exceed the power supply rails. If your math says the output should be 20 volts, but the op-amp is powered from plus and minus 15 volts, the real output saturates at about 15 volts. Exam questions do test saturation. Now let us go through the standard configurations. Memorize these gain formulas. Configuration 1. The inverting amplifier. The input source Vs connects through a resistor R1 to the inverting input. A feedback resistor Rf connects from the output back to the inverting input. The non-inverting input is grounded. Because the plus input is grounded, the minus input is a virtual ground at 0 volts. The current through R1 is therefore Vs minus 0 over R1, which is Vs over R1. That current cannot enter the op-amp, so all of it continues through Rf. The current through Rf is 0 minus Vout over Rf. Setting them equal, Vs over R1 equals negative Vout over Rf. So the gain is Vout over Vs equals negative Rf over R1. Inverting amplifier gain equals negative Rf over R1. The minus sign means the output is inverted 180 degrees out of phase with the input. Also note, the input resistance seen by the source is exactly R1, because the source drives into a virtual ground through R1. That is a downside of the inverting configuration. Configuration 2. The non-inverting amplifier. The input source connects directly to the non-inverting input. R1 runs from the inverting input to ground, and Rf runs from the output back to the inverting input. By Rule 2, the minus input equals the plus input, which equals Vin. The current through R1 is Vin over R1, flowing to ground. That same current comes from the output through Rf. So Vout equals Vin plus the drop across Rf, which is Vin plus Vin over R1 times Rf. Factor. Vout equals Vin times the quantity 1 plus Rf over R1. Non-inverting amplifier gain equals 1 plus Rf over R1. No minus sign. The output is in phase with the input. Note that this gain can never be less than 1. And note the input resistance is infinite, because the source connects straight to the op-amp input where no current flows. That is a major advantage. Configuration 3. The voltage follower, also called the unity gain buffer. Take the non-inverting amplifier, set Rf to 0, meaning a plain wire from output to inverting input, and set R1 to infinity, meaning nothing. The gain becomes 1 plus 0, which equals 1. So Vout equals Vin. Why build an amplifier with a gain of 1? Because of impedance. The follower has infinite input resistance and 0 output resistance. It lets a weak, high impedance source drive a heavy, low impedance load without being loaded down. It is a buffer. This is a favorite conceptual exam question, What is the purpose of a voltage follower? The answer is isolation and impedance buffering, not amplification. Configuration 4. The summing amplifier. Several inputs, V1, V2, V3, each through its own resistor R1, R2, R3, all meeting at the inverting input, with one feedback resistor RF and the plus input grounded. Because the inverting node is a virtual ground, each input contributes its own current independently, and KCL adds them. Vout equals negative RF times the quantity V1 over R1, plus V2 over R2, plus V3 over R3. If all input resistors are equal to R, this simplifies to Vout equals negative RF over R times the sum of the inputs. And if RF also equals R, you get a pure inverting adder. Vout equals the negative sum of the inputs. This is the basis of audio mixers and of digital to analog converters. Configuration 5. The difference amplifier, also called the subtractor. V1 enters through R1 to the inverting input, with R2 as feedback. V2 enters through R3 to the non-inverting input, with R4 from the plus input to ground. The general result is a little messy, but when the resistor ratios are matched, meaning R1 over R2 equals R3 over R4, it collapses beautifully. Vout equals R2 over R1 times the quantity V2 minus V1. And in the fully symmetric case where all four resistors are equal, Vout equals V2 minus V1, a pure subtractor. This is the front end of every instrumentation amplifier, used to reject common mode noise. Configuration 6. Cascaded stages. When op-amp stages are chained, output of one into input of the next, the overall gain is simply the product of the individual gains. Because each ideal op-amp has zero output resistance, the later stages do not load the earlier ones. So a stage of gain -5 followed by a stage of gain 3 gives an overall gain of -15. Multiply, do not add. Configuration 7. The integrator and the differentiator, in case they appear. Replace the feedback resistor of an inverting amplifier with a capacitor, and you get an integrator. Vout equals -1 over RC times the integral of V in dt. Replace the input resistor with a capacitor instead, and you get a differentiator. Vout equals -RC times the derivative of Vin with respect to time. Now let us do the practice problems. Practice pocket problem 8. Find the gain. The setup. A source Vs connects through a 5 kΩ resistor to the inverting input. A 25 kΩ resistor runs from the output back to the inverting input. A 10 kΩ resistor connects the non-inverting input to ground. The output is V0. Recognize the topology first. The signal enters through a resistor into the minus input, and the feedback returns to the minus input. That is an inverting amplifier. So the gain is -RF over R1, which is -25 over 5, which equals -5. AV equals -5. Now, the important part of this problem, the part it is actually testing. What does the 10 kΩ resistor do? Nothing. It has no effect on the gain whatsoever. Here's why. No current flows into the non-inverting input by golden rule 1. So no current flows through the 10 kΩ resistor. With no current, there is no voltage drop across it. So the non-inverting input sits at exactly 0 volts, ground, just as if the resistor were a plain wire. That resistor is there in real designs to balance the input bias currents of a non-ideal op-amp and reduce offset error. For ideal analysis, it is irrelevant. Exams put resistors like that in specifically to see whether you understand that no current flows into an op-amp input. Do not put it in your gain formula. Practice pocket problem 9. Find Vout. The setup. A 1-volt source drives a voltage divider made of a 10 kΩ resistor and a 90 kΩ resistor. The junction of that divider feeds the non-inverting input of the op-amp. From the inverting input, a 50 kΩ resistor goes to ground, and a 100 kΩ feedback resistor goes from the output back to the inverting input. The output drives a 10 kΩ load resistor, across which V0 appears. There is also an output current labeled I0. Step 1. Find the actual voltage at the op-amp input. The 1-volt source sees a divider of 10 kΩ and 90 kΩ. Crucially, the tap point feeds the non-inverting input, which draws 0 current. So the divider is unloaded, and the plain voltage divider formula applies exactly. The op-amp input is at the junction such that V in equals 1 volt times 90 over the quantity 90 plus 10. That is 1 times 90 over 100, which equals 0.9 volts. V in equals 0.9 volts. Step 2. Identify the amplifier configuration. The signal enters the non-inverting input directly. R1, from the inverting input to ground, is 50 kiloohms. Rf, the feedback resistor, is 100 kiloohms. That is a non-inverting amplifier. Gain equals 1 plus Rf over R1, which is 1 plus 100 over 50, which is 1 plus 2, which equals 3. AV equals 3. Step 3. Compute the output. V0 equals gain times input, which is 3 times 0.9, which equals 2.7 volts. V0 equals 2.7 volts. And notice again, the 10 kiloohm load resistor does not change V0 at all. Because the ideal op-amp has zero output resistance, it holds its output at 2.7 volts regardless of load. Load resistance affects the output current, not the output voltage. Step 4. The bonus. If the problem asks for I0, the op-amp output current, the output supplies two paths. First, the 10 kiloohm load, 2.7 volts divided by 10 kiloohms equals 0.27 milliamps. Second, the feedback chain, 100 kiloohms plus 50 kiloohms in series to ground, which is 150 kiloohms. 2.7 divided by 150 kiloohms equals 0.018 milliamps. Total output current is 0.27 plus 0.018, which equals 0.288 milliamps. That is where the current comes from, by the way, not from the input signal, from the power supply, through the op-amp. An op-amp is not a passive network. It is an active device that delivers power taken from its supply rails. Let me close with the op-amp problem-solving checklist. 1. Is there negative feedback from output to the minus input? If yes, apply the golden rules. If no, it is a comparator and the output slams to a rail. 2. Identify the configuration. Signal into the minus input means inverting. Signal into the plus input means non-inverting. 3. Find the actual voltage at the op-amp input terminals first, including any divider before the amplifier. 4. Apply the gain formula. 5. Check for saturation against the supply rails. 6. Ignore any resistor that carries no current, including a resistor from an input terminal to ground on the non-inverting side, and any load resistor on the output. Chapter 9. Capacitors and inductors, and practice pocket problems 10, 11, and 12. Up to now, every element has been a resistor, and everything was algebra. Capacitors and inductors introduce calculus because they store energy and their behavior depends on the rate of change of voltage or current. Let us take the capacitor first. A capacitor is two conducting plates separated by an insulator, called a dielectric. It stores energy in an electric field between the plates. Its capacitance C is measured in farads, abbreviated capital F. A farad is enormous, so real capacitors are in microfarads, nanofarads, and picofarads. The defining relationship of charge, Q equals C times V. Charge stored equals capacitance times voltage. Differentiate both sides with respect to time, remembering that current is the derivative of charge, and you get the current-voltage relationship. I equals C times dV dt. Say that out loud. Capacitor current equals C times the derivative of voltage. This one equation tells you everything about capacitor behavior. Consequence 1. If the voltage across a capacitor is constant, its derivative is 0, so the current is 0. A capacitor behaves as an open circuit to direct current. In steady-state DC, erase every capacitor and replace it with a break in the wire. Consequence 2. The voltage across a capacitor cannot change instantaneously. If it tried to jump, the derivative would be infinite, and the current would be infinite, which is physically impossible with any finite source. So capacitor voltage is continuous. This is the key fact for transient problems. V of C at time 0 plus equals V of C at time 0 minus. Consequence 3. Capacitor current, on the other hand, absolutely can jump instantaneously. Look at the graphs in problem 12. The current jumps from 5 amps to 0 to negative 10 amps with vertical edges. That is legal. Only the voltage must be continuous. The integral form, for when you know the current and want the voltage. V of t equals 1 over c times the integral of I dt plus the initial voltage V at t naught. Never forget that initial condition term. It is worth points. Energy stored in a capacitor, W equals 1/2 CV squared. Note it depends on voltage, not current, and note it is never negative. A capacitor can return energy to the circuit, but the stored energy itself is always positive or zero. Combinations. This is the reverse of resistors, and it is a classic exam trap. Capacitors in parallel add directly. C equivalent equals C1 plus C2. Because parallel plates in parallel means more plate area. Capacitors in series combine like resistors in parallel, using reciprocals. 1 over C equivalent equals 1 over C1 plus 1 over C2. And for exactly 2, product over sum. Say it out loud. Capacitors in parallel add. Capacitors in series do the reciprocal thing. That is backwards from resistors, and that is precisely why exams ask it. Now the inductor. An inductor is a coil of wire. It stores energy in a magnetic field. Its inductance L is measured in henries, abbreviated capital H. The defining relationship, flux linkage equals L times I. Differentiate, and you get the voltage-current relationship. V equals L times di dt. Inductor voltage equals L times the derivative of current. It is the exact dual of the capacitor. Consequence 1. If the current through an inductor is constant, its derivative is 0, so the voltage is 0. An inductor behaves as a short circuit to direct current. In steady-state DC, erase every inductor and replace it with a plain wire. Consequence 2. The current through an inductor cannot change instantaneously. A jump would require infinite voltage. So inductor current is continuous. I of L at time 0 plus equals I of L at time 0 minus. Consequence 3. Inductor voltage can jump instantaneously. That is exactly why you get a spark when you open a switch on an inductive load. The current is forced to change fast, and LdIdt produces an enormous voltage spike. The integral form, I of t equals 1 over L times the integral of V dt plus the initial current I at t naught. Energy stored in an inductor, W equals 1/2 Li squared. Depends on current, not voltage. Combinations. Inductors behave just like resistors. Inductors in series add. Inductors in parallel use reciprocals or product over sum for 2. So the memory hook is, inductors act like resistors for combining. Capacitors are the backwards ones. Let me lay out the duality table, because if you remember one column, you can derive the other. Capacitor and inductor. Voltage and current. C and L. I equals C dV dt and V equals L di dt. 1/2 CV squared and 1/2 Li squared. Open circuit at DC and short circuit at DC. Voltage is continuous and current is continuous. Parallel adds and series adds. Everything mirrors. Now, practice pocket problem 10. Find the current in a 150 microhenry inductor, given the voltage waveform. The waveform. From 0 to 2 microseconds, the voltage ramps linearly from 0 up to 15 volts. From 2 to 4 microseconds, the voltage is 0. From 4 to 5 microseconds, the voltage is negative 15 volts, constant. After 5 microseconds, 0. Since we are given voltage and asked for current in an inductor, we integrate. I of t equals 1 over L times the integral of V dt plus the initial current. Interval 1, 0 to 2 microseconds. First, write the voltage as a function of time. It rises from 0 to 15 volts in 2 microseconds, so the slope is 15 divided by 2 times 10 to the negative 6th, which equals 7.5 times 10 to the 6th volts per second. So V of t equals 7.5 times 10 to the 6th times t. Now integrate. I of t equals 1 over L times the integral from 0 to t of 7.5 times 10 to the 6th times tau, d tau. The integral of a linear ramp is 1/2 t squared. So we get 7.5 times 10 to the 6th, divided by 2 times 150 times 10 to the negative 6th, all multiplied by t squared. Compute the coefficient. 2 times 150 microhenries is 300 microhenries, which is 3 times 10 to the negative 4th. 7.5 times 10 to the 6th divided by 3 times 10 to the negative 4th equals 2.5 times 10 to the 10th. So I of t equals 25 times 10 to the ninth times t squared in amperes. That is a parabola, starting at 0 and curving upward. The initial current was 0 because the inductor was unenergized. At t equals 2 microseconds, 25 times 10 to the ninth times 2 times 10 to the negative sixth squared. 2 times 10 to the negative sixth squared is 4 times 10 to the negative 12th. Multiply. 25 times 10 to the ninth times 4 times 10 to the negative 12th equals 100 times 10 to the negative third, which equals 0.1 amperes. So at 2 microseconds the current has risen to 100 milliamps. Interval 2, 2 to 4 microseconds. The voltage is 0. Integrating 0 adds nothing. So the current holds constant at whatever it was. I of t equals 0.1 amperes, flat. This is important physically. An inductor with 0 volts across it is a short circuit, and current just keeps circulating unchanged. That flat top is exactly what the answer graph shows. Interval 3, 4 to 5 microseconds. The voltage is negative 15 volts. Integrating a constant gives a linear ramp, and since the constant is negative, the current ramps down. I of t equals 0.1 plus 1 over 150 microhenries times negative 15 times the quantity t minus 4 microseconds. Negative 15 divided by 150 times 10 to the negative sixth equals negative 1 times 10 to the fifth amperes per second. So I of t equals 0.1 minus 10 to the fifth times the quantity t minus 4 times 10 to the negative sixth. Expanding the constants, that is I of t equals 0.5 minus 10 to the fifth times t amperes. Check the endpoint. At t equals 5 microseconds, 0.5 minus 10 to the fifth times 5 times 10 to the negative sixth, which is 0.5 minus 0.5, which equals 0. The current returns to exactly 0 at 5 microseconds and stays there. That endpoint check is meaningful. The total area under the voltage curve is the total flux, and if the net area is 0, the final current must be 0. The positive triangle from 0 to 2 microseconds has area 1/2 times 2 microseconds times 15 volts, which is 15 microvolt seconds. The negative rectangle from 4 to 5 microseconds has area 1 microsecond times 15 volts, which is 15 microvolt seconds, negative. They cancel exactly. So the final current is 0. Always use that area argument as a check on inductor problems. The shape of the answer graph. A parabola rising from 0 to 0.1 amps over the first 2 microseconds. A flat plateau at 0.1 amps from 2 to 4 microseconds. Then a straight line falling from 0.1 to 0 between 4 and 5 microseconds. That is exactly the figure labeled B in your pocket. Practice pocket problem 11. Find the current in the circuit. The setup. A 10-volt source, a switch that closes at t equals 0, and a 2 Henry inductor. That is all. No resistance. Before the switch closes, no current flows, so the initial current I at 0 is 0. After the switch closes, the full 10 volts appears across the inductor. Apply the integral form. I of t equals 1 over L times the integral from 0 to t of 10 volts d tau, plus I of 0. 1 over 2 henries times 10 volts equals 5. The integral of a constant is that constant times t. So I of t equals 5t amperes, with t in seconds. The current ramps up linearly forever, at 5 amps per second, and grows without bound. That is the correct answer to the problem as stated, and it teaches an important idea. With a constant voltage across an ideal inductor and no resistance to limit it, the current increases linearly and without limit. In a real circuit, the wire resistance and the source's internal resistance eventually limit it, and you get the exponential RL response we will study in the next chapter. Note the initial condition explicitly, because graders look for it. I at t0 equals I at 0 equals 0, for t0 equal to 0. Practice pocket problem 12. Obtain the current, power, and energy for a 1 microfarad capacitor with the given voltage. The setup. A 1 microfarad capacitor driven by a voltage source. The voltage waveform is a trapezoid. It ramps linearly from 0 up to 10 volts over the interval 0 to 2 microseconds, holds flat at 10 volts from 2 to 4 microseconds, then ramps back down to 0 between 4 and 5 microseconds. Since we are given voltage and asked for current in a capacitor, we differentiate. I equals C dV dt, and C is 10 to the negative 6th farads. Interval 1, 0 to 2 microseconds. The voltage rises from 0 to 10 volts in 2 microseconds. Slope equals 10 over 2 times 10 to the negative 6th, which equals 5 times 10 to the 6th volts per second. So V of t equals 5 times 10 to the 6th times t. Then I equals C times dV dt equals 10 to the negative 6th times 5 times 10 to the 6th, which equals 5 amperes. Constant. Interval 2, 2 to 4 microseconds. The voltage is constant at 10 volts. The derivative of a constant is 0. So I equals 0 amperes. That confirms the rule. Constant voltage across a capacitor means 0 current, an open circuit. Interval 3, 4 to 5 microseconds. The voltage falls from 10 volts to 0 over 1 microsecond. The slope is negative 10 divided by 1 times 10 to the negative 6th, which equals negative 10 times 10 to the 6th volts per second. You can write the voltage as negative 10 times 10 to the 6th times the quantity t minus 5 microseconds, which correctly gives 10 volts at 4 microseconds and 0 at 5 microseconds. Then I equals 10 to the negative 6th times negative 10 times 10 to the 6th, which equals negative 10 amperes. So the current waveform is 5 amps flat for the first 2 microseconds, then 0 for 2 microseconds, then negative 10 amps for 1 microsecond, then 0 forever. All rectangular pulses with vertical edges, which is perfectly legal for capacitor current. And notice the areas. 5 amps for 2 microseconds is 10 microcoulombs of charge in. Negative 10 amps for 1 microsecond is 10 microcoulombs of charge out. Net charge 0, so the final voltage is 0. Charge balance is your check. Now power. Power is simply the product, P equals V times I, evaluated interval by interval. In interval 1, both voltage and current are positive, and the voltage is ramping, so power is a rising ramp. The capacitor is absorbing energy, charging up. In interval 2, the current is 0, so the power is 0. The capacitor is holding its charge, neither absorbing nor delivering. In interval 3, the voltage is positive but the current is negative, so the power is negative. Negative absorbed power means the capacitor is delivering energy back to the circuit. It is discharging, returning the energy it stored. That is the essential character of a storage element. Power positive while charging, power negative while discharging, and over a complete cycle the net energy is 0. A capacitor never dissipates energy. Only resistors do. Now energy. Use W equals 1/2 CV squared. Because it depends on V squared and the voltage is continuous, the energy curve is smooth with no jumps. In interval 1, the voltage is a linear ramp, so the energy goes as T squared. It curves upward from 0. In interval 2, the voltage is constant at 10 volts, so the energy is constant. 1/2 times 10 to the negative 6th times 10 squared equals 1/2 times 10 to the negative 6th times 100, which equals 50 microjoules. Flat. In interval 3, the voltage ramps down to 0, so the energy curves back down to 0, going as the square of the remaining voltage. The energy graph is therefore a smooth S-shaped rise to a plateau at 50 microjoules, then a smooth fall back to 0. That matches the last figure in your practice pocket exactly. Now, one note about the printed solution. The printed piecewise expressions for power and energy in your pocket use breakpoints at 1, 3, and 5 on a time axis labeled in seconds, and the peak power of 10 watts with plateau energy of 5 joules. Those come from the textbook's version of the same problem drawn on a rescaled time axis. The shapes are identical, and the shapes are what the exam will test. Power is a rising ramp, then 0, then a negative ramp returning to 0. Energy is a smooth rise, a flat plateau, and a smooth fall to 0. Learn the shapes and the method, and just be careful to use the actual numbers printed on whatever axis your exam gives you. Let me close this chapter with the 3 things most likely to be tested. 1. Which quantity is continuous? Capacitor voltage and inductor current. Those 2 never jump. Write that on your scratch paper the moment the exam starts. 2. What do they look like at DC steady state? Capacitor is an open circuit. Inductor is a short circuit. So to find any steady state condition, redraw the circuit with capacitors erased and inductors replaced with wires, then solve a plain resistive circuit. 3. Which direction is the calculus? Capacitor. Current is the derivative of voltage. Inductor. Voltage is the derivative of current. If you are given a waveform and asked for the other quantity, decide immediately whether you are differentiating, which turns ramps into steps, or integrating, which turns steps into ramps and ramps into parabolas. Chapter 10. First-order transients, RC and RL circuits. This topic is not in the practice pocket, but it follows directly from capacitors and inductors. It is standard cumulative final material, and it is highly formulaic, which means it is easy points if you know the recipe. Let us make sure you do. A first-order circuit is any circuit containing exactly one energy storage element, one capacitor or one inductor, plus resistors and sources. It is called first-order because the governing differential equation is first-order. The universal behavior, when something changes in a first-order circuit, typically a switch opening or closing, every voltage and every current in that circuit moves exponentially from its old value to its new value, with a single time constant. Here is the master formula. Memorize it exactly, because it solves every first-order transient problem in this course. X of t equals x final, plus the quantity x initial minus x final, times e to the power of negative t over tau. Let me say it in words. The response equals the final value, plus the difference between the initial value and the final value, decaying exponentially with time constant tau. Here, x can be any voltage or any current anywhere in the circuit. X initial is the value immediately after the switching instant, at t equals 0 plus. X final is the value the circuit settles into after a long time, at t equals infinity. And tau is the time constant. So to solve any first-order problem, you need exactly three numbers. Initial value, final value, time constant. Get those three, plug into the formula, and you are done. Three numbers every time. Now, how to get each one? The initial value. This is where the continuity rules earn their keep. First, analyze the circuit just before switching, at t equals 0 minus. Usually the circuit has been sitting in that configuration for a long time, so it is at DC steady state. Redraw with capacitors as open circuits and inductors as short circuits, and solve the resulting resistive circuit. From that, extract the one quantity that cannot jump, the capacitor voltage or the inductor current. Second, apply continuity. Capacitor voltage at 0 plus equals capacitor voltage at 0 minus. Inductor current at 0 plus equals inductor current at 0 minus. That carries one number across the switching instant. Third, redraw the circuit in its new configuration at t equals 0 plus, replacing the capacitor with a voltage source equal to its known voltage, or replacing the inductor with a current source equal to its known current. Then solve that resistive circuit for whatever quantity the problem is actually asking about. That gives you X initial for any variable, including the ones that do jump. The final value. Let the circuit sit in its new configuration forever. It reaches DC steady state again. So redraw with capacitors as opens and inductors as shorts, and solve. That gives X final. If the new configuration has no sources connected to the storage element, the final value is 0, and you have a pure natural response, a plain decaying exponential. The time constant. This is where students lose points, so listen closely. For an RC circuit, tau equals R times C. For an RL circuit, tau equals L divided by R. Note the difference. RC multiplies, L over R divides. Mixing those up inverts your answer. Say it out loud. Tau is RC, tau is L over R. But which R? Not just any resistor in the circuit. The R in the time constant formula is the Thevenin equivalent resistance seen by the storage element in the post-switching configuration. So the procedure is, remove the capacitor or inductor from the circuit, leaving two terminals. Deactivate the independent sources, shorting voltage sources, and opening current sources. Compute the equivalent resistance looking into those two terminals. That is your R. This is why Thevenin's theorem shows up again here. The storage element sees the rest of the circuit as a Thevenin equivalent, and it is our Thevenin that sets the time constant. Units check. Ohms times farads gives seconds. Henrys divided by ohms gives seconds. If your time constant does not come out in seconds, you made an error. Now, some physical intuition about the exponential. After one time constant, the response has completed about 63% of its total change. 63.2%, if you want the precise figure, because 1 minus e to the negative 1 is 0.632. After 2 time constants, about 86% complete. After 3 time constants, about 95% complete. After 4 time constants, about 98%. After 5 time constants, about 99.3%, which engineers universally treat as fully settled. So the rule of thumb is, a first-order circuit reaches steady state in about 5 time constants. That is a common short answer question. Also useful. The initial slope of the exponential, if extended as a straight line, would reach the final value in exactly 1 time constant. That is the graphical way to measure tau off an oscilloscope trace. Let us do a complete RC example. A 12-volt source in series with a 2 kilo-ohm resistor and a switch, feeding a capacitor of 100 microfarads that is initially uncharged. The switch closes at t equals 0. Find the capacitor voltage as a function of time. Initial value. The capacitor is uncharged, so Vc at 0 minus is 0, and by continuity Vc at 0 plus is also 0. X initial equals 0. Final value. After a long time, the capacitor is an open circuit, so no current flows, so no voltage drops across the 2 kilo-ohm resistor, so the full 12 volts appears across the capacitor. X final equals 12 volts. Time constant. Remove the capacitor. Kill the 12-volt source, replacing it with a short. Looking back into the terminals, we see just the 2 kilo-ohm resistor. So R equals 2000 ohms. Tau equals RC equals 2000 times 100 times 10 to the negative 6th, which equals 0.2 seconds. Plug into the master formula. Vc of t equals 12, plus the quantity 0 minus 12, times e to the negative t over 0.2. That is Vc of t equals 12 minus 12 e to the negative 5t, or equivalently 12 times the quantity 1 minus e to the negative 5t volts. That is the classic charging curve. Starts at 0, rises toward 12, reaching about 7.6 volts after 1 time constant of 0.2 seconds, and essentially all 12 volts after 1 second. And the current? I equals C dV dt equals 100 times 10 to the negative 6 times 12 times 5 times e to the negative 5t, which equals 6 times 10 to the negative 3rd times e to the negative 5t, that is 6 milliamps decaying exponentially. Check the initial current directly. At t equals 0 plus, the capacitor voltage is 0, so it acts momentarily like a short circuit, and the full 12 volts is across the 2 kilo-ohm resistor, giving 6 milliamps. Matches. Good. Notice the pattern. The capacitor voltage rose smoothly from 0. The capacitor current jumped instantly from 0 to 6 milliamps, and then decayed. Voltage continuous, current discontinuous. Exactly as the rules demand. Now in our L example. A 24-volt source, a 4-ohm resistor, and a 2 Henry inductor in series. The switch has been closed for a long time. At t equals 0, the switch opens, and the inductor now discharges through a separate 12-ohm resistor. Find the inductor current after switching. Initial value. Before switching, at steady state, the inductor is a short circuit, so the current is 24 divided by 4, which equals 6 amps. By continuity, IL at 0 plus is also 6 amps. X initial equals 6 amps. Final value. After switching, there is no source in the loop, so the current decays to 0. X final equals 0. Time constant. In the new configuration, the inductor sees the 12-ohm resistor. Tau equals L over R equals 2 over 12, which equals 0.1667 seconds. Master formula. IL of t equals 0, plus the quantity 6 minus 0, times e to the negative t over 0.1667. So IL of t equals 6 e to the negative 6t amperes. The voltage across the inductor at the instant of switching, V equals I times R equals 6 amps times 12 ohms, which is 72 volts. Note that this is 3 times the source voltage of 24 volts, and note its polarity is reversed. That is the inductive kick. Inductor current is continuous, so it must keep pushing 6 amps through whatever path is available, and whatever voltage that requires, it produces. This is the principle behind ignition coils and boost converters, and it is why you put a flyback diode across a relay coil. Let me also give you the 2 special names. because exam questions use the vocabulary. The natural response is the behavior with all independent sources removed, driven purely by the initial stored energy. It is a pure decaying exponential, x initial times e to the negative t over tau. The step response, or forced response plus natural response, is the behavior when a source is applied. That is the full master formula. The complete response equals the forced, or steady state, response plus the natural, or transient, response. The forced part is the final value. The natural part is the decaying term. Finally, a word about second-order circuits, in case your final touches on them. A circuit with both a capacitor and an inductor is second order, and its response can be overdamped, critically damped, or underdamped, depending on the relationship between the damping factor alpha and the resonant frequency omega naught. Overdamped means two real exponentials and a sluggish return with no overshoot. Critically damped is the fastest response with no overshoot. Underdamped means a decaying sinusoid, that is, ringing with overshoot. For a series RLC circuit, alpha equals R over 2L, and omega naught equals 1 over the square root of LC. For a parallel RLC, alpha equals 1 over 2 RC, with the same omega naught. If alpha is greater than omega naught, overdamped. If equal, critically damped. If less, underdamped. Know the vocabulary and know that the damping comes from resistance. If your final covers second-order circuits, that framework plus the initial condition machinery from this chapter is most of what you need. Recap the recipe one more time because it is worth points on any transient question. Find the initial value, using steady state before switching plus the continuity rule. Find the final value, using steady state after switching. Find the time constant, using the Thevenin resistance seen by the storage element, with RC for capacitors and L over R for inductors. Plug into final plus the difference of initial minus final times e to the negative t over tau. Then get any other quantity from that one using Ohm's law, KVL, and KCL. Chapter 11. Number Systems and Binary Arithmetic. The second half of ECE1004 is the computer engineering half, and it begins with number systems. This is guaranteed exam material, and it is pure procedure, so there is no excuse for losing points here. A positional number system has a base, also called a radix. Each digit position carries a weight equal to the base raised to the power of the position index, counting from 0 at the rightmost digit of the integer part, and going negative to the right of the radix point. Decimal is base 10, digits 0 through 9. Binary is base 2, digits 0 and 1 only. Each binary digit is called a bit. Octal is base 8, digits 0 through 7. Hexadecimal is base 16, digits 0 through 9. Then A, B, C, D, E, F, representing 10, 11, 12, 13, 14, and 15. You should know the powers of 2 by heart, at least up to 2 to the 16th. Let me recite them. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64. 2 to the seventh is 128. 2 to the eighth is 256. 2 to the ninth is 512. 2 to the 10th is 1024. 2 to the 11th is 2048. 2 to the 12th is 4096. 2 to the 13th is 8192. 2 to the 14th is 16,384. 2 to the 15th is 32,768. 2 to the 16th is 65,536. Also know the hexadecimal to binary table cold because it makes conversion instant. 0 is 0000. 1 is 0001. 2 is 0010. 3 is 0011. 4 is 0100. 5 is 0101. 6 is 0110. 7 is 0111. 8 is 1000. 9 is 1001. A is 1010, that is 10. B is 1011, 11. C is 1100, 12. D is 1101, 13. E is 1110, 14. F is 1111, 15. Now the conversions. converting any base to decimal. Multiply each digit by its positional weight and add. Example, binary 101101. Reading from the left, the weights are 32, 16, 8, 4, 2, 1. The bits are 1, 0, 1, 1, 0, 1. So we take 32 plus 0 plus 8 plus 4 plus 0 plus 1, which equals 45. So binary 101101 equals 45 in decimal. Example, hexadecimal 2a. That is 2 times 16 plus 10 times 1, which is 32 plus 10, which equals 42. Converting decimal to binary. There are two methods. Method 1, repeated division by 2. Divide the number by 2, write down the remainder, then divide the quotient by 2, write down that remainder, and keep going until the quotient is 0. Then read the remainders in reverse order, from last to first. Example, convert 45 to binary. 45 divided by 2 is 22, remainder 1. 22 divided by 2 is 11, remainder 0. 11 divided by 2 is 5, remainder 1. 5 divided by 2 is 2, remainder 1. 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0, remainder 1. Now read the remainders backwards. 1, 0, 1, 1, 0, 1. So 45 is 101101 in binary, which matches our earlier conversion. Method 2. Subtract the largest power of 2. Find the largest power of 2 that fits. Write a 1 in that position, subtract it, repeat. 445, 32 fits, remainder 13. 16 does not fit, write 0. 8 fits, remainder 5. 4 fits, remainder 1. 2 does not fit, write 0. 1 fits, remainder 0. Bits, 101101. Same answer, and for most people this method is faster. Converting a fraction from decimal to binary uses repeated multiplication by 2 instead. Multiply the fractional part by 2, record the integer part that pops out, keep the remaining fraction, and repeat. Read the recorded digits top to bottom, in forward order this time. Example, convert 0.625 to binary. 0.625 times 2 is 1.25. Record 1, keep 0.25. 0.25 times 2 is 0.5. Record 0, keep 0.5. 0.5 times 2 is 1.0. Record 1, keep 0. Done. Reading forward, 1, 0, 1. So 0.625 equals 0.101 in binary. Check. 1/2 plus 0 plus 1/8 equals 0.625. Correct. Converting binary to hexadecimal and back. This is the easy one, and it is worth doing instantly. Binary to hex. Group the bits into groups of 4, starting from the radix point and working outward. Pad with leading zeros if necessary. Convert each group of 4 to 1 hex digit. Example, binary 101101. Group from the right, 0101, and the leftover is 10, which pads to 0010. So we have 0010, which is 2, and 1101, which is D. So the answer is 2D. And 2D in decimal is 2 times 16 plus 13, which is 45. Consistent with everything above. Hex to binary. Expand each hex digit into its 4-bit pattern. That is it. Binary to octal is the same idea with groups of 3 bits instead of 4, since 8 is 2 cubed. Now, representing negative numbers. This is where the real exam questions lie. There are 3 schemes, and you must be able to distinguish them. Scheme 1. Sign and magnitude. The leftmost bit is a sign bit, 0 for positive and 1 for negative, and the remaining bits are the plain magnitude. So in 8 bits, positive 5 is 0000101, and negative 5 is 1000101. Simple to read, but it has 2 representations of 0, positive 0 and negative 0, and the arithmetic hardware is awkward, rarely used. Scheme 2. One's complement. To negate a number, flip every bit. So negative 5 and 8 bits is 11111010. This also has 2 zeros, all zeros and all ones. Also mostly historical. Scheme 3. 2's complement. This is what every real computer uses, and this is what your exam will test. To form the 2's complement negative of a number, flip every bit, then add 1. Say it out loud, invert and add 1. Example, represent -5 in 8-bit 2's complement. Start with +5, 0, 0, 0, 0, 0, 1, 0, 1. Flip every bit, 1, 1, 1, 1, 1, 0, 1, 0. Add 1, 1, 1, 1, 1, 1, 0, 1, 1. So -5 is 1, 1, 1, 1, 1, 0, 1, 1. An equivalent shortcut that is faster by hand. Starting from the right, copy bits up to and including the first one you encounter, then flip everything to the left of it. For 5, which is 0, 0, 0, 0, 0, 1, 0, 1, copy the rightmost one, then flip everything left of it. 0, 0, 0, 1, 0 becomes 1, 1, 1, 1, 1, 0, 1. Put it together, 1, 1, 1, 1, 1, 0, 1, 1. Same answer, and much faster. The properties of 2's complement that get tested. Property 1. The leftmost bit is still a sign indicator. If it is 1, the number is negative. If 0, non-negative. Property 2. There is exactly one representation of 0. That is the whole advantage. Property 3. The range for n bits is from -2 to the power of n-1 up to +2 to the power n-1, -1. So 8 bits covers -128 through +127. 16 bits covers -32,768 through +32,767. Notice the asymmetry, one more negative value than positive values. That is because 0 occupies a slot on the positive side. Property 4. Addition and subtraction use the exact same hardware. To subtract, you negate the second operand and add. That is why 2's complement 1. Property 5. To find the decimal value of a 2's complement number directly, use the same positional weights, but make the leftmost weight negative. For 8 bits, the weights are -128, then 64, 32, 16, 8, 4, 2, 1. Let us check. 1, 1, 1, 1, 1, 0, 1, 1. That is -128 plus 64 plus 32 plus 16 plus 8 plus 0 plus 2 plus 1. Sum the positives. 64 plus 32 is 96, plus 16 is 112, plus 8 is 120, plus 2 is 122, plus 1 is 123. Then -128 plus 123 equals -5. Correct. Now, binary addition. The rules for a single column. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. And with an incoming carry, 1 plus 1 plus 1 is 1, carry 1. Example, add binary 1011, which is 11, and binary 0110, which is 6. Rightmost column, 1 plus 0 is 1. Next, 1 plus 1 is 0, carry 1. Next, 0 plus 1 plus the carry 1 is 0, carry 1. Next, 1 plus 0 plus carry 1 is 0, carry 1. So we get 10001, which is 17. And 11 plus 6 equals 17. Correct. Now overflow, which is a favorite exam topic and is widely misunderstood. Overflow means the true result does not fit in the available number of bits. But the test for overflow depends on whether you are doing signed or unsigned arithmetic. For unsigned arithmetic, overflow occurs when there is a carry out of the leftmost bit position. That is it. For signed 2's complement arithmetic, a carry out of the leftmost bit means nothing at all. Instead, signed overflow occurs when you add two numbers of the same sign and get a result of the opposite sign. Adding two positives and getting a negative is overflow. Adding two negatives and getting a positive is overflow. Adding a positive and a negative can never overflow, because the result is always between the two operands. The equivalent hardware rule. Signed overflow occurs when the carry into the signed bit position differs from the carry out of the signed bit position. If they are the same, no overflow. If they differ, overflow. That is implemented as an exclusive or of those two carries. Example, in 4-bit 2's complement, add 0101, which is 5, and 0100, which is 4. The result is 1001, which in 4-bit 2's complement reads as -7. Two positives gave a negative, so that is overflow. And indeed, 9 does not fit in 4-bit signed, which only reaches 7. One more concept: sign extension. If you want to widen a 2's complement number from 4 bits to 8 bits, you copy the sign bit into all the new positions. So 1001, -7 in 4 bits, becomes 11111001 in 8 bits, which is still -7. You do not pad with zeros for signed numbers. Padding with zeros is correct only for unsigned. Finally, 2 coding schemes that sometimes appear. BCD, binary coded decimal. Each decimal digit is separately encoded in 4 bits. So the number 45 is encoded as 0100, then 0101. Notice this is not the same as the binary for 45. BCD wastes the codes for 10 through 15, but makes decimal display trivial. ASCII, the American Standard Code for Information Interchange. A 7-bit code for characters. The one fact worth knowing is that the digit characters 0 through 9 occupy codes 48 through 57 decimal, uppercase A through Z occupy 65 through 90, and lowercase a through Z occupy 97 through 122. So the difference between an uppercase and lowercase letter is exactly 32, which is a single bit, bit 5. That is why case conversion is a 1-bit operation. Also know your units of storage. A bit is 1 binary digit. A nibble is 4 bits. A byte is 8 bits. A word is machine-dependent, commonly 32 or 64 bits. And within bits you can represent 2 to the n distinct values, which means to encode m distinct items you need at least the ceiling of log base 2 of m bits. 6 items need 3 bits, because 2 squared is only 4, but 2 cubed is 8. Chapter 12. Logic gates, Boolean algebra, and practice pocket problem 7. Boolean algebra is the mathematics of 2-valued logic. Every variable is either 0 or 1, false or true, low or high. There are exactly 3 fundamental operations, and everything else is built from them. The AND operation, written as a dot, or as simple juxtaposition, like AB. The output is 1 only when every input is 1, and behaves like multiplication. 0 and anything is 0. 1 and A is A. The OR operation, written as a plus sign, like a plus B. The output is 1 when at least one input is 1, or behaves somewhat like addition, but with the crucial difference that 1 plus 1 equals 1, not 2. 1 or anything is 1. 0 or A is A. The NOT operation, also called complement or inversion, written as a bar over the variable, or sometimes an apostrophe after it. It flips 0 to 1 and 1 to 0. From these 3, we build the standard gates. The AND gate. Symbol is a D shape, flat on the left, rounded on the right. Output is 1 only if all inputs are 1. The OR gate. Symbol is a curved shield shape with a concave input side and a pointed output. Output is 1 if any input is 1. The NOT gate, or inverter. Symbol is a triangle with a small circle, called a bubble, at its output tip. That bubble always means inversion, wherever you see it. The NAND gate. An AND gate with a bubble on the output. Output is 0 only when all inputs are 1. It is not AND. The NOR gate. An OR gate with a bubble on the output. Output is 1 only when all inputs are 0. It is not OR. The exclusive OR gate, or XOR. Symbol is an OR gate with an extra curved line at the input. Output is 1 when the inputs differ. For 2 inputs, a XOR B equals A B bar plus A bar B. Think of it as an inequality detector, or as a 1-bit adder without carry, or as a controllable inverter. If one input is 0, the output equals the other input, and if one input is 1, the output is the inverse of the other input. The exclusive NOR gate, or XNOR. XOR with a bubble. Output is 1 when the inputs are the same. It is an equality detector, also called a comparator. Now, the universality property, which is a common conceptual question. NAND is a universal gate. You can build any logic function using nothing but NAND gates. A NOT is a NAND with both inputs tied together. An AND is a NAND followed by a NOT, which is another NAND. An OR is a NAND with both inputs inverted first, by De Morgan. So 3 ways to build all 3 fundamental operations from NAND alone. NOR is also universal, by the dual argument. Why do we care? Because in CMOS technology, NAND and NOR gates are actually simpler and faster to fabricate than and/or gates. An AND gate is physically built as a NAND followed by an inverter, so designs are often converted entirely into NAND form. Now the laws of Boolean algebra. Learn these as a list you can recite. Identity. A plus 0 equals A. A times 1 equals A. Null, or annihilation. A plus 1 equals 1. A times 0 equals 0. Idempotence. A plus A equals A. A times A equals A. Complement. A plus a bar equals 1. A times A bar equals 0. Double negation. The complement of the complement of A equals A. Commutative. A plus B equals B plus A. AB equals BA. Associative. A plus the quantity B plus C equals the quantity A plus B plus C. Same for AND. Distributive. There are two, and the second one surprises people. The first, A times the quantity B plus C equals AB plus AC. That is the familiar one, just like ordinary algebra. The second, A plus the quantity B times C equals the quantity A plus B times the quantity A plus C. That one has no counterpart in ordinary arithmetic, but it is valid in Boolean algebra, and it is how you convert between sum of products and product of sums form. Absorption. A plus AB equals A, and A times the quantity A plus B equals A. In words, if a term is already covered by a simpler term, the more complicated one adds nothing. The other absorption, sometimes called the redundancy law. A plus a bar B equals A plus B, and A times the quantity A bar plus B equals AB. This one is very useful and easy to forget. Consensus theorem. AB plus a bar C plus BC equals just AB plus a bar C. The third term, BC, is redundant. Why? Because if B and C are both 1, then either A is 1, in which case AB covers it, or A is 0, in which case A bar C covers it. So BC never contributes anything new. The consensus term is the one formed from the two other terms by removing the variable that appears in both true and complemented form. Remember this one, because K-maps sometimes hide it, and it is a common source of non-minimal answers. And now the most important pair of identities in all of digital logic. De Morgan's laws. Law 1. The complement of the quantity A plus B equals A bar times B bar, not of an or equals and of the knots. Law 2. The complement of the quantity A times B equals A bar plus B bar, not of an and equals or of the knots. The way to remember it, break the bar and change the sign. Break the long over bar into two separate bars and flip the operator between them, and becomes or becomes and. De Morgan's laws extend to any number of variables, and they work in both directions. Graphically, they say a NAND gate is equivalent to an OR gate with bubbles on both inputs, and a NOR gate is equivalent to an AND gate with bubbles on both inputs. Being able to slide bubbles across a gate and flip its shape is called bubble pushing, and it is how experienced designers convert circuits to NAND-only form quickly. The duality principle. Every Boolean identity has a dual, obtained by swapping and with or and swapping 0 with 1, while leaving the variables unchanged. If the original is true, the dual is true. That is why the laws above come in pairs. Now let us do practice pocket problem 7. The expression is F equals A, B bar, C, plus ABC, plus the quantity C plus D, times the quantity D bar plus E. Part A asks you to draw the gate diagram of that expression as written. Let me describe it, since you are listening rather than looking. You need an inverter on B to produce B bar, and an inverter on D to produce D bar. Then a 3-input and gate taking A, B bar, and C. That produces the first term. A second 3-input and gate taking A, B, and C. That produces the second term. An OR gate taking C and D, producing C plus D. A second OR gate taking D bar and E, producing D bar plus E. A 2-input and gate combining the outputs of those two OR gates, producing the product term. And finally, a 3-input OR gate combining the first and output, the second and output, and that product, producing F. That is 9 gates total, counting the 2 inverters. Direct implementation, no simplification. Part B asks you to simplify and redraw. Step 1. Handle the first 2 terms. AB bar C plus ABC. Factor out the common AC. That gives AC times the quantity B bar plus B. and b bar plus b equals 1 by the complement law. Anything or its own complement is 1. So those two terms collapse to AC times 1, which is just AC. That is the single most valuable pattern in Boolean simplification. Whenever you see two product terms that are identical except that one variable appears complemented in one and uncomplemented in the other, that variable drops out entirely. That is exactly what a K-map adjacency represents. Step 2. Expand the product of sums. The quantity C plus D times the quantity D bar plus E. Multiply it out just like ordinary algebra, using the distributive law. C times D bar gives CD bar. C times E gives CE. D times D bar gives DD bar. D times E gives DE. Now, D times D bar equals 0 by the complement law. A variable ANDed with its own complement is always 0, and 0 ORed into a sum contributes nothing, so it vanishes. So that product becomes CD bar plus CE plus DE. Step 3. Assemble. F equals AC plus CD bar plus CE plus DE. Step 4. Factor, which is the form your practice pocket presents. 3 of those terms contain C. Factor it out. F equals C times the quantity of plus D bar plus E plus DE. That is the answer as printed in your solution, and it is correct. It uses 2 inverters and far fewer gates than the original. Now let me show you something extra, because your solution says other solutions are also possible, and a sharp grader might reward this. Look at the sum of products form again. AC plus CD bar plus CE plus DE. Focus on 3 of those terms, CD bar plus DE plus CE. That is exactly the consensus theorem pattern. Take D as the pivot variable. We have D bar ANDed with C and D ANDed with E, and then the term CE, which is formed from the leftovers of the other two. The consensus theorem says that third term is redundant. Let me prove it to you by cases, since you cannot see a K-map while driving. Suppose CE equals 1, meaning both C and E are 1. Then look at D. If D is 0, then D bar is 1. So the term CD bar equals 1, and the expression is already 1. If D is 1, then DE equals 1, and the expression is already 1. Either way, whenever CE is 1, the expression is already 1 without it. Therefore, CE never adds anything, and we can delete it. So the truly minimal sum of products is F equals AC plus CD bar plus DE. 3 product terms, 6 literals. Or factored, F equals C times the quantity of plus D bar plus DE. That implementation needs 1 inverter for D, 2 2-input and gates, and 1 more 2-input and gate, and a 3-input or gate. Notice that B disappeared entirely from the function, which means the output does not depend on B at all. Recognizing that a variable has dropped out is itself worth mentioning in your answer. Now let us cover the canonical forms, because exam questions ask for them by name. A literal is a variable or its complement. A appearing is 1 literal. A bar is also 1 literal. A minterm is a product term that contains every variable in the function exactly once, either true or complemented. For 3 variables A, B, C, the minterm for the combination A equals 1, B equals 0, C equals 1 is AB bar C. Minterms are numbered by the binary value of the input combination they detect. AB bar C corresponds to 101, which is 5, so it is minterm 5, written M sub 5. A maxterm is a sum term containing every variable exactly once. Maxterm number 5 for 3 variables is a bar plus B plus C bar. Notice the inversion. For maxterms, a variable appears complemented when its bit is 1, the opposite of minterms. Sum of products, or SOP, is an or of in terms. Canonical sum of products means every term is a full minterm. This form maps directly onto a 2-level and or circuit, and it is the form K-maps produce naturally. Product of sums, or POS, is in and of or terms. Canonical product of sums means every term is a full maxterm. This maps onto a 2-level or in circuit. To go from a truth table to canonical sum of products, write 1 minterm for every row where the output is 1 and OR them together. To go from a truth table to canonical product of sums, write 1 maxterm for every row where the output is 0 and end them together. The relationship. If a function is the sum of a certain set of minterm numbers, then its complement is the sum of all the other minterm numbers. And the same function expressed as a product of maxterms uses exactly the maxterm numbers that are missing from the minterm list. So the minterm list and the maxterm list are complementary sets over the same index range. Finally, a note on gate counting and cost. Since exams sometimes ask which implementation is better, the standard measures are number of gate inputs, which is the total literal and term count, and the number of logic levels, which determines propagation delay. A two-level implementation, meaning and then or, is the fastest possible for a general function, but may require more gates. A factored, multi-level implementation uses fewer gates, but adds delay. That is the fundamental area versus speed trade-off in digital design, and it is a legitimate short answer question. Chapter 13. Carnot maps and digital building blocks. The Carnot map, or K-map, is a graphical method for minimizing Boolean functions. It is essentially a truth table rearranged so that logically adjacent combinations are physically adjacent, which makes simplification visual instead of algebraic. Since you are listening rather than looking, let me describe the structure precisely, and then give you the rules, which are the part that actually gets tested. A two-variable K-map is a 2x2 grid for cells, 1 per minterm. A three-variable K-map is a 2x4 grid, 8 cells. A four-variable K-map is a 4x4 grid, 16 cells. Beyond four variables, K-maps get unwieldy, and you use a tabular method or software. The essential property: the row and column labels are arranged in gray code order, not binary counting order. Gray code means only one bit changes between adjacent entries. For a four-variable map, the column labels go 0, 0, 0, 1, 1, 1, 1, 0. Notice it is not 0, 0, 0, 1, 1, 0, 1, 1. The order 1, 1 before 1, 0 is deliberate, so that each step changes exactly one bit. Because of that ordering, physically adjacent cells differ in exactly one variable, which means they can be combined and that variable eliminated. That is the whole trick. Now the rules for grouping. Rule 1. Group cells containing ones in rectangular groups whose size is a power of 2, 1, 2, 4, 8, or 16 cells. No group of 3, no group of 6, no L shapes, no diagonals. Rule 2. Groups must be rectangular, and they may wrap around the edges of the map. The left edge is adjacent to the right edge. The top edge is adjacent to the bottom edge. The four corners of a four-variable map are all mutually adjacent and can form a single group of 4. This wraparound is the number one thing students forget. Rule 3. Groups may overlap. Reusing a 1 in more than one group is not only allowed, it is often necessary. Rule 4. Make each group as large as possible. A larger group means fewer variables in the resulting product term. A group of 1 gives a term with all the variables. A group of 2 eliminates one variable. A group of 4 eliminates 2 variables. A group of 8 eliminates 3 variables. Every doubling of group size removes one more literal. Rule 5. Use as few groups as possible, while still covering every one at least once. Rule 6. Reading off a group. Look at which variables stay constant across every cell in the group. Those variables appear in the product term. A variable that is constantly 1 appears uncomplemented. A variable that is constantly 0 appears complemented. Any variable that changes within the group is eliminated. Then, or all the group terms together, and you have the minimal sum of products. The vocabulary that exam questions use. An implicant is any product term that implies the function, meaning any valid group. A prime implicant is a group that cannot be made any larger. You should always expand groups to prime implicants. An essential prime implicant is a prime implicant that covers at least one minterm not covered by any other prime implicant. Essential prime implicants must appear in the final answer, no choice about it. The efficient procedure: find all prime implicants, identify the essential ones, and commit to them. Then choose the fewest additional prime implicants needed to cover whatever ones remain. Note that a minimal solution is not always unique. Two different covers can have the same cost. If your answer differs from the key but has the same number of terms and literals and is logically equivalent, it is correct. Don't care conditions. Sometimes certain input combinations can never occur, or their output genuinely does not matter. These are marked with an X or AD on the map. You may treat each don't care as either a 1 or a 0, whichever helps you make bigger groups. Use them to enlarge groups, but never make a group consisting only of don't cares. A classic example is BCD inputs, where the combinations for 10 through 15 never occur, giving you 6 free don't cares that dramatically simplify 7-segment decoder logic. To get a product of sums from a K-map instead, group the zeros rather than the ones. Read each group as a sum term with the polarity of every variable flipped and in the results. That gives you the minimal POS directly. Equivalently, minimize the complement of the function and then apply De Morgan. Now let us cover the standard combinational building blocks, which are near certain to appear at least as a definition question. The half adder adds 2 single bits. Its outputs are sum and carry. Sum equals a XOR B, carry equals A and B. 2 gates, done. The full adder adds 3 single bits, A, B, and a carry in. Its outputs are sum and carry out. Sum equals a XOR B XOR C in. Carry out equals AB plus C in times the quantity A XOR B. Or equivalently, AB plus AC in plus BC in, which reads as carry out is 1 when at least 2 of the 3 inputs are 1. A majority function. The ripple carry adder. Chain in full adders. Carry out of each feeding carry in of the next. Simple, but slow, because the carry has to propagate all the way from the least significant bit to the most significant bit. That is why fast machines use carry look-ahead adders, which compute all the carries in parallel using generate and propagate signals. Generate equals AB. Propagate equals a XOR B, or sometimes A plus B. Then carry out of stage I equals generate I, plus propagate I times carry in of stage I, expanded recursively. Subtraction. To compute a minus B in 2's complement, invert every bit of B and add, with the carry in of the least significant stage set to 1. That plus 1 is what completes the 2's complement negation. So the same adder hardware does both operations, controlled by one signal. If that control line is called sub, then you feed each B bit through an XOR gate with sub, and you also feed sub into the carry in. When sub is 0, the XOR passes B through and the carry in is 0, so you add. When sub is 1, the XOR inverts B and the carry in is 1, so you subtract. That single elegant circuit is worth understanding. The multiplexer, or MUX, a data selector. It has 2 to the n data inputs, n select lines, and 1 output. The select lines choose which data input is routed to the output. A 4-to-1 MUX has 4 data inputs and 2 select lines. A key fact, a multiplexer can implement any Boolean function by wiring the function's truth table values into the data inputs and the variables into the select lines. That is a common exam problem. The demultiplexer, or demux. The reverse. 1 data input, n select lines, 2 to the n outputs. Routes the input to the chosen output. The decoder. N inputs, 2 to the n outputs, exactly one of which is active at a time, corresponding to the binary value of the input. A 3 to 8 decoder takes 3 bits and activates one of 8 lines. Decoders are how memory address lines select a particular row. Note that a decoder output is exactly a minterm. So a decoder plus an OR gate implements any function directly from its minterm list. The encoder, the reverse of a decoder. 2 to the n inputs, n outputs, producing the binary index of whichever input is active. A priority encoder resolves the case where multiple inputs are active by outputting the index of the highest priority one, which is what makes it usable in real interrupt controllers. The comparator compares 2 multi-bit numbers and outputs whether A is greater than, equal to, or less than B. Equality is built from XNOR gates on each bit position, AND together. Now, a brief word on sequential logic, in case your final reaches that far. Combinational logic has outputs that depend only on the present inputs. Sequential logic has outputs that depend on the present inputs and on stored state, that is, on history. The storage elements are latches and flip-flops. The S are latch, set, and reset inputs. Setting S makes the output 1. Setting R makes the output 0. Asserting both simultaneously is the forbidden or invalid state, because the 2 outputs, which should be complements, both go to the same value. and the resulting state when you release is unpredictable. Built from two cross-coupled NOR gates, or two cross-coupled NAND gates. The D latch. One data input D and an enable. While enable is high, the output follows D transparently. When enable goes low, the output holds the last value. Level sensitive. The D flip-flop. Same idea, but edge triggered. The output takes the value of D only at the instant of a clock edge, usually the rising edge, and holds it otherwise. Edge triggering is what makes synchronous design possible, because every storage element in the machine updates at exactly the same instant. The JK flip-flop. Like an SR, but the forbidden combination is redefined. J equals 1 and K equals 1 causes the output to toggle. J alone sets, K alone resets, neither holds. The T flip-flop. Toggle. When T is 1, the output flips on each clock edge. When T is 0, it holds. Made from AJK with J and K tied together. Chains of T flip-flops make ripple counters, and each stage divides the frequency by 2. Timing terms you should be able to define. Setup time is the interval before the clock edge during which the data input must already be stable. Hold time is the interval after the clock edge during which it must remain stable. Propagation delay is the time from the clock edge until the output actually changes. Violating setup or hold produces metastability, an output that hovers between valid levels for an unpredictable time. And the maximum clock frequency of a synchronous system is set by the longest path, clock-to-output propagation delay, plus the worst-case combinational logic delay, plus the setup time of the receiving flip-flop. That sum must fit inside one clock period. Finally, the two classic state machine styles. In a Moore machine, the outputs depend only on the current state. In a Mealy machine, the outputs depend on the current state and the current inputs. Moore outputs are glitch-free and change only on clock edges. Mealy machines usually need fewer states, but their outputs can react within a cycle. If a question asks the difference, that is the answer. Moore, state only. Mealy, state and input. Chapter 14. Sinusoids, phasors, impedance, and AC power. If your cumulative final reaches into alternating current analysis, this chapter is your coverage. Even if it does not, the vocabulary here shows up in conceptual questions, so it is worth the 20 minutes. A sinusoid is written as V of t equals Vm times cosine of the quantity omega t plus phi. Vm is the amplitude, also called the peak value. Omega is the angular frequency, in radians per second. Phi is the phase angle, usually stated in degrees. The relationships you must know. Omega equals 2 pi f, where f is the frequency in hertz. And the period t equals 1 over f. So omega equals 2 pi over t. 460 hertz, the North American power frequency. The period is 1 over 60, about 16.7 milliseconds, and omega is 377 radians per second. Memorize 377. It appears constantly, leading and lagging. If one sinusoid reaches its peak earlier in time than another, it leads. If later, it lags. Comparing V equals cosine of omega t and I equals cosine of the quantity omega t minus 30 degrees. The current lags the voltage by 30 degrees. Always compare two sinusoids of the same frequency, written in the same form, both as cosines with positive amplitudes. Convert if necessary. Sine of theta equals cosine of the quantity theta minus 90 degrees. So sine lags cosine by 90 degrees. Our ms value. Root mean square, also called the effective value. It is the DC value that would deliver the same average power to a resistor. For any sinusoid, VRMS equals Vm divided by the square root of 2, which is Vm times 0.707. So when we say household power is 120 volts, that is our ms. The actual peak is 120 times the square root of 2, which is about 170 volts. And the peak-to-peak is about 340 volts. Average power in a resistor is VRMS squared over R, or IRMS squared times R. Always use our ms for power calculations. Using peak values gives you an answer that is off by a factor of 2. Note also that the average value of a full sinusoid over a complete cycle is 0, while its our ms value is not. Average and our ms are different questions. Now, phasors. This is the technique that turns differential equations into algebra. A phasor is a complex number that encodes the amplitude and phase of a sinusoid, with the frequency understood and suppressed. If v of t equals Vm cosine of the quantity omega t plus phi, then the phasor is capital V equals Vm at an angle of phi. In rectangular form, that is Vm cosine phi plus j Vm sine phi, where j is the square root of -1. Electrical engineers use j instead of I, because I is already taken by current. The magic of phasors, differentiation in the time domain becomes multiplication by j omega in the phasor domain, and integration becomes division by j omega. That converts every circuit differential equation into an algebraic equation with complex numbers. Impedance, symbol capital Z, is the phasor domain generalization of resistance. It is the ratio of phasor voltage to phasor current, and it is a complex number measured in ohms. For a resistor, Z equals R, purely real. Voltage and current are in phase. For an inductor, Z equals J omega L, purely imaginary and positive. The voltage leads the current by 90 degrees. Note that impedance grows with frequency, so an inductor blocks high frequencies and passes DC, consistent with it being a short circuit at DC where omega is 0. For a capacitor, Z equals 1 over J omega C, which equals negative J over omega C, purely imaginary and negative. The current leads the voltage by 90 degrees. Impedance falls with frequency, so a capacitor blocks DC and passes high frequencies, consistent with it being an open circuit at DC. The memory device for phase relationships is the mnemonic ELI, the ICE man. In an inductor, which is L, voltage E leads current I. In a capacitor, which is C, current I leads voltage E, ELI, the ICE man. Impedance is written Z equals R plus JX, where R is resistance and X is reactance. Positive reactance is inductive. Negative reactance is capacitive. Admittance, symbol capital Y, is the reciprocal of impedance and equals G plus JB, conductance plus susceptance. The enormous payoff. Once everything is an impedance, all of your DC techniques work unchanged. Impedances in series add. Impedances in parallel combine by reciprocals or product over sum. Voltage dividers, current dividers, nodal analysis, mesh analysis, superposition, Thevenin, and Norton, all of them work identically, just with complex arithmetic instead of real arithmetic. That is the entire point of the phasor method. You learn no new circuit theory, only new algebra. A quick complex number refresher for the arithmetic. Rectangular form is a plus JB. Polar form is magnitude at an angle theta. The magnitude equals the square root of a squared plus b squared. The angle equals the arctangent of b over a, adjusted for quadrant. Going back, a equals magnitude times cosine theta, b equals magnitude times sine theta. The practical rule: add and subtract in rectangular form. Multiply and divide in polar form, where you multiply magnitudes and add angles, or divide magnitudes and subtract angles. Switching forms strategically saves an enormous amount of time. Now, AC power. 3 quantities, and students confuse them constantly. Real power, symbol capital P, measured in watts. This is actual power converted to useful work or heat. P equals V RMS times I RMS times cosine of theta, where theta is the angle by which the voltage leads the current, which is the same as the impedance angle. Reactive power, symbol capital Q, measured in volt-amperes reactive, abbreviated VAR. This is power that sloshes back and forth between the source and the reactive elements without being consumed. Q equals V RMS times I RMS times sine theta. Inductive loads have positive Q, capacitive loads have negative Q. Apparent power, symbol capital S, measured in volt-amperes, or VA. It is simply the product of the RMS voltage and RMS current, ignoring phase. S equals V RMS times I RMS. It is what determines the required current rating of your wires and transformers, which is why transformers are rated in kilovolt amperes, not kilowatts. The power triangle relates them. S squared equals P squared plus Q squared. Real power is the horizontal leg. Reactive power is the vertical leg. Apparent power is the hypotenuse. The power factor is the ratio of real power to apparent power. Power factor equals cosine theta equals P over S. It ranges from 0 to 1. A power factor of 1 means a purely resistive load. All the delivered current is doing useful work. A power factor near 0 means the load is almost purely reactive and the utility is pushing a lot of current for very little useful work. Power factor is described as lagging when the current lags the voltage, which happens with inductive loads, which is most industrial equipment because motors are inductive. It is leading when the current leads, which happens with capacitive loads. Power factor correction is the practice of adding capacitors in parallel with an inductive load to cancel its reactive power, bringing the power factor closer to 1. This reduces the current the utility must supply, reduces line losses, and avoids utility penalty charges. If a question asks why factories install capacitor banks, that is your answer. Complex power, symbol capital S as a complex quantity, equals P plus JQ. It also equals the phasor voltage times the complex conjugate of the phasor current, divided by 2 if you are using peak amplitudes rather than our MS. Watch that factor of 2. If your phasors are in our MS, no factor of 2. If they are in peak amplitude, divide by 2. Finally, a few frequency response concepts, since they follow directly from impedance. A low-pass filter passes low frequencies and attenuates high ones. The simplest is a resistor in series with a capacitor taking the output across the capacitor. Its cutoff frequency, where the output power falls to half, is F equals 1 over 2 pi RC. A high-pass filter is the same components with the output taken across the resistor instead. Same cutoff formula. The cutoff, or corner, or half power frequency, is where the magnitude falls to 1 over the square root of 2, which is 0.707 of its maximum. In decibels, that is a drop of 3 decibels, which is why it is called the 3 dB point. Decibels. Power gain in decibels equals 10 times the base 10 logarithm of the power ratio. Voltage gain in decibels equals 20 times the base 10 logarithm of the voltage ratio. Note the 10 versus 20. Power uses 10, voltage and current use 20, because power goes as the square. A factor of 2 in power is 3 decibels. A factor of 2 in voltage is 6 decibels. A factor of 10 in voltage is 20 decibels. Resonance. In a series RLC circuit, at the resonant frequency the inductive and capacitive reactances cancel exactly. The impedance is purely resistive and at its minimum, and the current is at its maximum. The resonant frequency is omega naught equals 1 over the square root of LC. The quality factor Q describes the sharpness of the resonance, and the bandwidth equals omega naught divided by Q. Higher Q means a narrower, sharper peak. That is how a radio tunes to one station and rejects the others. Chapter 15. The Spoken Formula Sheet, an Exam Strategy. This chapter is a straight recitation of everything you need to have memorized, followed by strategy. Listen to it more than once. Repetition is the point. Basic quantities. Current equals the derivative of charge with respect to time. Charge equals the integral of current. Voltage equals energy per unit charge. Power equals voltage times current. Energy equals the integral of power. Ohm's law. Voltage equals current times resistance. Conductance equals 1 over resistance, measured in Siemens. Power in a resistor, 3 forms. V times I squared times R, and V squared over R. Kirchhoff's current law. The sum of currents entering a node is 0. Kirchhoff's voltage law. The sum of voltages around a loop is 0. Combinations. Resistors in series add. Resistors in parallel use reciprocals or product over sum for exactly 2. Capacitors in parallel add. Capacitors in series use reciprocals. Inductors in series add. Inductors in parallel use reciprocals. Remember, capacitors are the backwards ones. Voltage divider. The voltage across R1 equals the total voltage times R1 over the sum of the series resistances. Same resistor on top. Current divider. For 2 resistors. The current through R1 equals the total current times R2 over the sum. Other resistor on top. Delta to Y. Each Y resistor equals the product of the 2 adjacent delta resistors divided by the sum of all 3. Y to delta. Each delta resistor equals the sum of the pairwise products of the Y resistors divided by the opposite one. Balanced case. Our delta equals 3 times our Y. Analysis methods. Nodal analysis. Pick a ground. Write KCL at each remaining node. The current leaving node A toward node B through resistance R equals VA minus VB over R. Voltage source between two non-reference nodes means supernode. 1 KCL around the bubble, plus the constraint that the node voltage difference equals the source value. Mesh analysis. All mesh currents clockwise. Write KVL per mesh. A shared resistor contributes R times my mesh current minus the neighbors. A current source alone in one mesh sets that mesh current directly. A current source shared between two meshes means supermesh. 1 KVL around the outer perimeter, plus the constraint that the mesh current difference equals the source value. Source transformation. A voltage source V in series with R equals a current source V over R in parallel with R. The arrow points toward the plus terminal. Only valid when the resistor is genuinely in series or genuinely in parallel. Superposition. One independent source at a time. Voltage sources off means shorted. Current sources off means opened. Never deactivate dependent sources. Never superpose power. Thevenin. V Thevenin is the open circuit voltage. R Thevenin is the resistance looking in with independent sources killed, or the open circuit voltage divided by the short circuit current, or the ratio of a test voltage to a test current. Norton. I Norton is the short circuit current. R Norton equals R Thevenin. And V Thevenin equals I Norton times R Thevenin. Maximum power transfer. Load resistance equals R Thevenin. Maximum power equals V Thevenin squared divided by 4 R Thevenin. Efficiency at the match is 50%. Storage elements. Capacitor. Charge equals C versus current equals C times dV dt. Energy equals 1/2 CV squared. Open circuit at DC. Voltage cannot jump. Inductor. Voltage equals L times d I dt. Energy equals 1/2 Li squared. Short circuit at DC. Current cannot jump. First order transients. The response equals the final value, plus the quantity initial minus final, times e to the negative t over tau. Tau equals RC for a capacitor. Tau equals L over R for an inductor. R is the Thevenin resistance seen by the storage element after switching. 63% after one-time constant. 95% after 3. Settled after 5. Op-amps. Golden rules. No current into either input, and with negative feedback the two input voltages are equal. Inverting gain equals negative RF over R1. Non-inverting gain equals 1 plus RF over R1. Voltage follower gain equals 1, used for buffering. Summing amplifier. Negative RF times the sum of each input over its own resistor. Difference amplifier with matched ratios. R2 over R1 times the quantity V2 minus V1. Cascaded stages. Multiply the gains. The output cannot exceed the supply rails. AC. Omega equals 2 pi F. Period equals 1 over F. RMS equals peak over the square root of 2. Impedance of a resistor is R. Of an inductor, J omega L. Of a capacitor, 1 over J omega C. EL I the IC E man. In an inductor voltage leads current. In a capacitor current leads voltage. Real power equals VRMS times IRMS times cosine theta. Apparent power equals VRMS times IRMS. Power factor equals cosine theta equals P over S. S squared equals P squared plus Q squared. Digital. Powers of 2 through 2 to the 16th, which is 65,536. Decimal to binary by repeated division by 2. Reading remainders backwards. Binary to hex by grouping 4 bits. 2's complement. Invert and add 1. Range for n bits is -2 to the n minus 1 through +2 to the n minus 1 minus 1. Signed overflow. Same signs in, different sign out. Sign extension. Copy the sign bit leftward. De Morgan. The complement of a plus b equals a bar times b bar. The complement of ab equals a bar plus b bar. Break the bar, change the sign. A plus a bar equals 1. A times a bar equals 0. Absorption. A plus ab equals a. And a plus a bar, b equals a plus b. Consensus. ab plus a bar c plus bc equals ab plus a bar c. NAND and NOR are each universal. XOR outputs 1 when inputs differ. XNOR outputs 1 when they match. K-map groups must be rectangular, sized in powers of 2, may wrap around edges, may overlap, and should be as large as possible. Half adder, sum is a XOR B, carry is A and B. Full adder, sum is the XOR of all three, carry out is the majority function. A decoder output is a minterm. A multiplexer can implement any function. Now, exam strategy. Strategy 1. In the first 90 seconds, before you solve anything, write your formula dump on the scratch paper or the margin. Ohm's law, the divider rules, series and parallel, the op-amp gains, the transient master formula, tau equals RC and L over R, De Morgan, 2's complement. Getting those out of your head and onto paper frees your working memory for the actual problems, and it protects you against panic-induced blanking. Strategy 2. Read the entire exam before starting. Do the problems you know cold first, in order of confidence, not in order of numbering. Banking easy points early builds momentum and guarantees you are not still working on problem 1 when time expires. Strategy 3. On every circuit problem, before writing an equation, label everything. Mark the polarity of every voltage you intend to compute. Mark the direction of every current. Give every node a name. Most lost points come from sign confusion, and labeling first eliminates most of that. Strategy 4. Choose your method deliberately. Count nodes and count meshes. Ask whether Thevenin or source transformation would shortcut the work. 30 seconds of method selection routinely saves 5 minutes of algebra. Strategy 5. Sanity check every result before moving on. Is the parallel resistance smaller than the smallest branch? Is the resistor power positive? Do the branch currents at a junction add up? Do the series voltage drops add up to the total? Is the magnitude physically reasonable? Does the op-amp output exceed the supply rails? Each of these takes about 5 seconds, and each has caught real errors. Strategy 6. Carry units through every step. If your time constant does not come out in seconds, or your power in watts, you have a numerical error. And unit consistency is often worth partial credit even when the arithmetic is wrong. Strategy 7. Show your method clearly, box your answers, and never erase work. Partial credit is real. If you set up the correct 3 equations and then make an arithmetic slip, you may still earn most of the points, but only if the grader can follow what you did. A page of correct setup with a wrong final number scores far better than a bare wrong number. Strategy 8. If you get stuck, write down what you do know. Write the constraint equations. Write the topology observations. Write the method you would use. Then move on and come back. An unstarted problem earns 0. A partially set up problem does not. Strategy 9. Watch for the deliberate distractors. The resistor from an op-amp's non-inverting input to ground that carries no current. The load resistor that does not affect an ideal op-amp's output voltage. The variable that drops out of a Boolean expression entirely. The element shorted by a wire. Exams put these in on purpose, and recognizing them quickly is a skill you can practice. Strategy 10. Budget your time by point value, not by difficulty. If a problem is worth 10% of the exam, it deserves 10% of the time and no more. When you hit your budget, mark it, move on, and return if there is time left. Now, the top 10 mistakes students actually make on this exam. Listen to these as a warning list. 1. Using the voltage divider formula on resistors that are not actually in series, because something taps off between them. 2. Putting the same resistor on top in the current divider. Remember, current divider uses the other resistor. 3. Forgetting that product over sum only works for exactly 2 resistors in parallel. 4. Mixing kiloohms and ohms in the same equation. 5. Sign errors from inconsistent mesh current directions. Always clockwise. 6. Writing KCL with some terms entering and some leaving. Always leaving. 7. Forgetting the constraint equation for a supernode or a supermesh, leaving you 1 equation short. 8. Confusing tau equals RC with tau equals L over R. 9. Applying superposition to power. 10. Forgetting to add 1 after inverting in 2's complement. And a bonus 11th. Solving the circuit perfectly and then not answering the question that was asked. Reread the question after you finish. Every time. Chapter 16. Rapid Fire Drill, Part 1. Circuits. Here's how this works. I ask a question. Then there is a short silence, a few seconds, for you to answer out loud. Then I give the answer. Say your answer out loud, actually out loud, even in the car. Speaking the answer forces retrieval, and retrieval is what builds memory. Silently thinking I know that one does almost nothing. If you miss one, do not stop and worry about it. Just note it and keep going. You can replay this chapter as many times as you like. Let us begin. Question 1. State Ohm's law. Voltage equals current times resistance. V equals IR. Question 2. What are the three formulas for power dissipated in a resistor? V times I squared times R, and V squared divided by R. Question 3. What does Kirchhoff's current law say, and what physical principle is it? The sum of currents entering a node equals 0. It is conservation of charge. Question 4. What does Kirchhoff's voltage law say, and what physical principle is it? The sum of voltages around any closed loop equals 0. It is conservation of energy. Question 5. Two resistors in series carry the same watt. The same current. Series elements share current. Question 6. Two resistors in parallel share the same watt. The same voltage. Parallel elements share voltage. Question 7. What is the equivalent of a 49 ohm and a 51 ohm resistor in series? 100 ohms. Series resistances, just add. Question 8. What is the equivalent of two 100 ohm resistors in parallel? Mm. 50 ohms. N identical resistors in parallel give R over N. Question 9. What is the equivalent of a 60 ohm and a 15 ohm resistor in parallel? Mm. 12 ohms. 60 times 15 is 900. Divided by 75 is 12. Question 10. In the voltage divider, which resistor goes in the numerator? Mm. 12. The same resistor whose voltage you want. Same on top. Question 11. In the current divider with two resistors, which resistor goes in the numerator? The other one. Current divider uses the opposite resistor because current prefers the smaller resistance. Question 12. When is product over sum valid? Only for exactly two resistors in parallel, never for three. Question 13. A parallel combination is always compared to the smallest branch how? It is always smaller than the smallest branch. If it is not, you made an error. Question 14. What is the voltage across a short circuit? 0 volts. Always, regardless of current. Question 15. What is the current through an open circuit? 0 amps. Always, regardless of voltage. Question 16. Nodal analysis is based on which of Kirchhoff's laws? 0 Kirchhoff's current law. Nodes and currents. Question 17. Mesh analysis is based on which law? 0 Kirchhoff's voltage law. Loops and voltages. Question 18. In nodal analysis, what is the expression for the current leaving node A toward node B through resistance R? 0 VA minus VB, all over R. Here minus there, over R. Question 19. When do you need a supernode? 0 When a voltage source sits between two non-reference nodes, so neither node voltage is known individually. Question 20. A supernode gives you how many equations? 0 0 2. 1 kcl around the bubble, plus 1 constraint equation from the source. Question 21. In what direction should you assign all mesh currents? Clockwise. All of them, every time. Question 22. What is the current through a resistor shared between mesh 1 and mesh 2, as seen from mesh 1? I1 minus I2. My mesh current minus the neighbors. Question 23. When do you need a supermesh? When a current source sits in a branch shared between two meshes. Question 24. If a current source sits alone in a single mesh, what do you do? You write that mesh current down immediately as equal to the source value. No KVL equation needed for that mesh. One free unknown eliminated. Question 25. How do you deactivate a voltage source? Replace it with a short circuit. A wire. Question 26. How do you deactivate a current source? Replace it with an open circuit. A break. Question 27. Do you ever deactivate a dependent source in superposition? Never. Dependent sources stay active in every subcircuit. Question 28. Can you apply superposition to power? No. Power is not linear. It involves a square. Superpose voltages and currents, then compute power at the end. Question 29. In a source transformation, which direction does the current source arrow point? Toward the terminal that was the positive terminal of the voltage source. The arrow points to the plus. Question 30. Convert a 180-volt source in series with 90 ohms into a current source form. Two amps in parallel with 90 ohms. 180 divided by 90 is 2. Question 31. What is V Thevenin physically? The open circuit voltage at the terminals, with the load removed. Question 32. What is I Norton physically? The short circuit current through the terminals. Question 33. Give the relationship between the Thevenin and Norton equivalents. V Thevenin equals I Norton times R, and the resistance is the same in both. Question 34. Name the method for finding our Thevenin that works even when dependent sources are present. Divide the open circuit voltage by the short circuit current, or apply a test source and take the ratio of test voltage to test current. Question 35. State the maximum power transfer condition. The load resistance must equal the Thevenin resistance of the source network. Question 36. What is the formula for the maximum power delivered? V Thevenin squared, divided by 4 times R Thevenin. Question 37. What is the efficiency at maximum power transfer? Mm. 50%. The Thevenin resistance burns exactly as much as the load. Question 38. For the practice pocket problem 5 circuit, what were V Thevenin and R Thevenin at terminals A and B? Mm. 90 volts and 45 ohms, which gives 1.5 amps into the 15 ohm load. Question 39. State the 2 golden rules of the ideal op amp. No current flows into either input. And with negative feedback, the plus input voltage equals the minus input voltage. Question 40. What is the gain of an inverting amplifier? Negative RF over R1. Question 41. What is the gain of a non-inverting amplifier? Mm. 1 plus RF over R1. Question 42. An op amp has a 25 kiloohm feedback resistor and a 5 kiloohm input resistor in inverting configuration. What is the gain? Mm. 5. Question 43. An op amp has a 100 kiloohm feedback resistor and a 50 kiloohm resistor to ground in non-inverting configuration. What is the gain? 3. 1 plus 100 over 50. Question 44. What is the gain of a voltage follower, and why would you use one? The gain is 1. You use it for impedance buffering to let a weak source drive a heavy load without being loaded down. Question 45. Two stages in cascade have gains of -5 and 3. What is the overall gain? -15. Cascade gains multiply. Question 46. Does a load resistor on an ideal op-amp output change the output voltage? No. The ideal op-amp has zero output resistance. The load changes the output current, not the output voltage. Question 47. Write the capacitor current voltage relationship. I equals C times dV dt. Current is C times the derivative of voltage. Question 48. Write the inductor voltage current relationship. V equals L times d I dt. Voltage is L times the derivative of current. Question 49. Which quantity cannot change instantaneously in a capacitor? The voltage. Capacitor voltage is continuous. Question 50. Which quantity cannot change instantaneously in an inductor? The current. Inductor current is continuous. Question 51. What does a capacitor look like at DC steady state? An open circuit. Question 52. What does an inductor look like at DC steady state? A short circuit. Question 53. Energy stored in a capacitor? One half CV squared. Question 54. Energy stored in an inductor? One half Li squared. Question 55. How do capacitors combine in parallel? They add directly. That is backwards from resistors. Question 56. How do capacitors combine in series? By reciprocals or product over sum for 2. Again, backwards from resistors. Question 57. How do inductors combine? Exactly like resistors. Series adds. Parallel uses reciprocals. Question 58. State the master formula for any first-order transient. X of t equals x final, plus the quantity x initial minus x final, times e to the negative t over tau. Question 59. What is tau for an RC circuit? R times C. Question 60. What is tau for an RL circuit? L divided by R. Question 61. Which R do you use in the time constant? The Thevenin resistance seen by the storage element in the configuration after switching. Question 62. What percentage of the total change is complete after one time constant? About 63%. Question 63. After how many time constants do we call the circuit settled? Five. About 99.3% complete. Question 64. A capacitor is uncharged and a switch connects it through a resistor to a source. What is the capacitor's behavior at the instant of switching? It momentarily behaves like a short circuit because its voltage is zero and cannot jump. So the initial current is the source voltage divided by the resistance. Question 65. An inductor has been carrying steady current, and the switch opens. What does it do? It maintains its current, producing whatever voltage that requires, which can be a very large spike. That is the inductive kick. Question 66. What is the RMS value of a sinusoid with peak amplitude Vm? Vm divided by the square root of 2, which is 0.707 times Vm. Question 67. What is the impedance of an inductor? J omega L. Question 68. What is the impedance of a capacitor? One over j omega c, which equals negative j over omega c. Question 69. Recite the phase mnemonic and explain it. ELI the ICE man. In an inductor, voltage leads current. In a capacitor, current leads voltage. Question 70. Define power factor. The cosine of the phase angle between voltage and current. Equivalently, real power divided by apparent power. That is the end of part 1. Let it settle for a minute, and then part 2 covers digital logic. Chapter 17. Rapid fire drill, part 2. Digital logic and closing. Same rules. Question, short silence. Answer out loud, then I confirm. Question 1. How many values can be represented with n bits? Two to the n. Question 2. What is 2 to the 10th? 1024. Question 3. What is 2 to the 16th? Mm. 65,536. Question 4. Convert binary 101101 to decimal. 45. 32 plus 8 plus 4 plus 1. Question 5. Convert decimal 45 to hexadecimal. 2D. Group the binary as 00101101. Question 6. What is the fastest way to convert binary to hexadecimal? 5. Group the bits in fours starting from the radix point and convert each group to one hex digit. Question 7. How many bits does one hexadecimal digit represent? 5. For bits, and one octal digit represents 3 bits. Question 8. Convert decimal to binary. Describe the method. Repeatedly divide by 2. Record the remainders, then read the remainders in reverse order. Or subtract the largest fitting powers of 2. Question 9. How do you form the 2's complement of a binary number? 5. Invert every bit, then add 1. Question 10. Give the 8-bit 2's complement representation of -5. 111111011. Question 11. What is the range of an 8-bit 2's complement number? 5. -128 through +127. Question 12. Why is the 2's complement range asymmetric? 5. Because there is only one representation of 0, and it occupies a slot on the non-negative side. Question 13. What is the main advantage of 2's complement over sign and magnitude? One representation of 0, and subtraction uses the same hardware as addition. Question 14. How do you detect overflow in sign 2's complement addition? Adding two numbers of the same sign produces a result of the opposite sign. Equivalently, the carry into the sign bit differs from the carry out of it. Question 15. Does a carry out of the most significant bit indicate signed overflow? No, that indicates in signed overflow. For signed numbers, it means nothing by itself. Question 16. How do you widen a 2's complement number from 4 bits to 8? Sign extension. Copy the sign bit into all the new leading positions. Question 17. What is the output of an AND gate? One only when every input is 1. Question 18. What is the output of an OR gate? One only when every input is 0. Question 19. When does an XOR gate output 1? When its inputs differ. Question 20. When does an XNOR gate output 1? When its inputs are the same. It is an equality detector. Question 21. Name the two universal gates. NAND and NOR. Either one alone can build any logic function. Question 22. How do you make an inverter out of a single NAND gate? Tie both of its inputs together. Question 23. State De Morgan's first law. The complement of A plus B equals of bar times B bar. Not of an or is the end of the knots. Question 24. State De Morgan's second law. The complement of AB equals of bar plus B bar. Not of an and is the or of the knots. Question 25. Give the shorthand for remembering De Morgan. Break the bar, change the sign. Question 26. Simplify a plus a bar. 1. Question 27. Simplify a times a bar. 0. Question 28. Simplify a plus a b. Just a. That is absorption. Question 29. Simplify a plus a bar b. A plus b. That is the other absorption identity. Question 30. Simplify ABC plus AB bar C. AC. The variable that appears both ways drops out. Question 31. State the consensus theorem. AB plus a bar C plus BC equals AB plus a bar C. The third term is redundant. Question 32. What does the quantity C plus D times the quantity D bar plus E expand to? CD bar plus CE plus DE, because D times D bar is 0 and drops out. Question 33. Fully simplify the practice pocket function f equals 8b bar C plus ABC plus the quantity C plus D times the quantity D bar plus E. A C plus CD bar plus CE plus DE, which factors to C times the quantity of plus D bar plus E plus DE. And by the consensus theorem, the CE term is actually redundant. giving the minimal form AC plus CD bar plus DE. Question 34. In that function, does the output depend on B? No. B cancels out completely. Question 35. What is a minterm? A product term containing every variable of the function exactly once, true or complemented. Question 36. What is a max term? A sum term containing every variable exactly once. Question 37. How do you build a canonical sum of products from a truth table? Write one minterm for every row where the output is 1 and OR them together. Question 38. How do you build a canonical product of sums from a truth table? Write one max term for every row where the output is 0 and end them together. Question 39. Why are K-map rows and columns labeled in gray code order? So that physically adjacent cells differ in exactly one variable, which is what allows them to be combined. Question 40. What sizes may a K-map group be? Powers of 2 only. 1, 2, 4, 8, or 16. Rectangular, never L-shaped or diagonal. Question 41. Can K-map groups wrap around the edges of the map? Yes. Left wraps to right, top wraps to bottom, and all 4 corners are mutually adjacent. Question 42. Can K-map groups overlap? Yes, and often they must. Question 43. How many variables does a group of 8 cells eliminate? Three. Every doubling of group size eliminates one more variable. Question 44. What is an essential prime implicant? A prime implicant that covers at least one minterm covered by no other prime implicant. It must appear in the final answer. Question 45. How do you use don't care conditions? Treat each one as a 0 or a 1, whichever makes your groups larger. But never form a group made only of don't cares. Question 46. How do you read a minimal product of sums off a K-map? Group the zeros instead of the ones, and write each group as a sum term with every variable's polarity flipped. Question 47. Give the half-adder equations. Sum equals a XOR B. Carry equals A and B. Question 48. Give the full adder some equation. Sum equals Azor B XOR carry in. Question 49. Describe the full adder carry out in words. It is 1 when at least 2 of the 3 inputs are 1. It is a majority function. Question 50. What is the drawback of a ripple carry adder? The carry must propagate through every stage, so the delay grows linearly with the number of bits. Question 51. How do you turn an adder into a subtractor? Invert the bits of the second operand with XOR gates, and set the least significant carry into 1. That completes the 2's complement negation. Question 52. How many select lines does an 8 to 1 multiplexer have? Three. 2 cubed is 8. Question 53. How many outputs does a 3 to 8 decoder have? And how many are active at once? Eight outputs, exactly 1 active at a time. Question 54. What Boolean object does a single decoder output correspond to? A minterm, which is why a decoder plus an OR gate implements any function from its minterm list. Question 55. What is the difference between combinational and sequential logic? Combinational outputs depend only on present inputs. Sequential outputs also depend on stored state, that is, on history. Question 56. What is the forbidden input condition of an SR latch? Set and reset both asserted at the same time. The resulting state is indeterminate when they are released. Question 57. What is the difference between a latch and a flip-flop? A latch is level-sensitive and transparent while enabled. A flip-flop is edge-triggered and captures only at a clock edge. Question 58. What does a JK flip-flop do when both J and K are 1? It toggles. Question 59. Define setup time and hold time. Setup time is how long the data must be stable before the clock edge. Hold time is how long it must remain stable after the clock edge. Question 60. What is the difference between a Moore machine and a Mealy machine? Moore outputs depend only on the current state. Mealy outputs depend on the current state and the current inputs. That is the end of the drill. Now, the closing. Let me leave you with the small number of things that, if you know nothing else, will earn you the most points on this exam. 1. Ohm's law and the 3 power formulas. They appear in nearly every problem. 2. Series adds. Parallel is product over sum for 2, and a parallel combination is always smaller than the smallest branch. 3. Voltage divider puts the same resistor on top. Current divider puts the other one on top. 4. Nodal analysis is KCL with the pattern here minus there over R. Mesh analysis is KVL with all currents clockwise and shared resistors written as mine minus the neighbor's. 5. A voltage source between 2 non-reference nodes means supernode. A current source between 2 meshes means supermesh. Each gives 1 KCL or KVL plus 1 constraint. 6. Thevenin, open circuit voltage, and the resistance looking in with independent sources killed. Voltage sources short, current sources open. 7. Op amps, no current into the inputs, and the 2 inputs are at the same voltage. Inverting gain is negative RF over R1. Non-inverting is 1 plus RF over R1. 8. Capacitor voltage and inductor current are the 2 things that cannot jump. Capacitor is open at DC, inductor is short at DC. 9. Transients. Final plus initial minus final times the decaying exponential. Tau is RC, or L over R. 10. 2's complement is invert and add 1. De Morgan is break the bar and change the sign. And in Boolean algebra, whenever a variable appears both true and complemented across otherwise identical terms, it drops out. Now some practical advice for the last 24 hours. Do not learn new material the night before. Consolidate what you have. Rework the practice pocket problems from a blank page without looking at the solutions and see whether you can reproduce them. Sleep. A rested brain retrieves formulas that a tired brain cannot. Sleep deprivation costs more points than an extra hour of studying gains. That is not motivational advice. It is a measurable effect. Bring a calculator you have actually used before and know how it handles parentheses and scientific notation. Bring a spare battery if it takes one. In the first 90 seconds of the exam, dump your formulas onto the paper. Then read the whole exam. Then start with the problem you are most confident about. Label every polarity and every current direction before writing a single equation. Check every answer with a 5-second sanity test. Is the parallel resistance smaller than the smallest branch? Is the resistor power positive? Do the currents at a node sum to 0? Do the series drops add to the total? And answer the question that was actually asked. You have done the work. The material in this recording is not that large a set of ideas. It is about 10 core relationships applied in different combinations. You know them now. Go take the exam. Good luck.